heterogeneous computing and the CPU on OpenCL. Then we'll have a break, 30-minute break. And then Chris Lamb from Nvidia will come talk about OpenCL on Nvidia GPUs. And Eric Schenk from EA will come talk about game developers' views on OpenCL. And then Kari Pulli from Nokia will come talk about OpenCL on handheld devices. Then we'll have a little panel session where you can ask questions. And so start thinking about questions you'd like to ask during that panel session, and please hold the questions for the panel. So what's OpenCL? Well, it's a new standard for heterogeneous parallel computing that lets you leverage some of the new highly parallel processors like GPUs. So for example, you can now write applications using OpenCL which allow you to do true hybrid or heterogeneous co-processing, where one application does parts of its work on a multi-core CPU and parts of its work on a highly parallel GPU. And it also works for other devices like Cell and some other sorts of parallel kinds of processors. And this thing has really gone through some pretty rapid changes and very rapid pace of development and adoption. The spec was published last December, and you'll see the progress that has been made by various companies trying to pull this whole thing together. So with no further ado, let me have Neil Trevett come up. So Neil is Vice President at Nvidia. He's in charge of mobile content. He's also president of the Khronos Group, which is a standards organization. He's worked at part of Khronos. He's worked on the OpenGL ES and OpenCode working groups. He chairs the OpenCL working group that's defining industry standards for advanced computing and graphics and media processing. So here's Neil.
Great, thank you, John. Let me start by saying it's actually been a blast and an honor working on OpenCL. As John said, it's a fast-moving project, and it's been a pleasure working with the other members of the working group within Khronos, and you'll get the chance to meet some of those working group members this afternoon. We felt it was appropriate to start this afternoon's session by giving you some context on why is OpenCL being created, who is creating it, and the industry background. But we're going to keep this part of the session pretty short. We'll get through it quickly, and then the other presenters will get into more technical detail. So who is the Khronos Group? The Khronos Group is the group that's driving the development and the evolution of OpenCL. Khronos is an open standards consortium. We create standards that are available to the industry royalty-free. I like to say that Khronos is standards by the industry, for the industry. It's a forum where any company can join. It's a safe forum with a good, well-defined IP framework that companies can cooperate freely to create open standards that make market and product opportunities so the members in the industry can go away and make more money. We have a particular focus on defining API standards that define how software accesses and leverages silicon acceleration, with a particular focus on graphics and media and compute acceleration APIs. We tend to stick quite close to the silicon. We try to be strongly commercially focused. We try not to do research projects. We try to focus our resources and efforts on API standards that are going to have an impact on products and the industry. But we are committed to royalty-free. We don't try to make money out of the standards. We try to enable the industry and our members to leverage these standards to go and make money by selling awesome products that use the standards. We have about 120 members, so we're quite broadly represented in the industry. All of the key silicon vendors are members, application vendors, OS vendors, OEMs from the desktop and mobile spaces, carriers, application developers, tools developers, everyone has a voice, and any of these members can participate in any of the working groups that Khronos is running. So it's important that we have this good representation. It not only gives us the skill set to create standards that do meet the problems that need to be solved, it also gives us a good mechanism for getting these standards, once they're complete, out into the industry and drive their adoption in a commercially significant way. So what about OpenCL? The OpenCL was catalyzed by the realization that GPUs and CPUs are gradually getting an increasingly high amount of overlapping capability. CPUs are getting more and more cores. GPUs have always been highly parallel, but they're becoming more and more programmable. And so there's this intersection emerging where we need to be able to have a single programming framework that can be used to program either type of architecture. CPUs have had good standards that are specifically for their kinds of architecture, such as OpenMP. GPUs have had shading languages for a few years now to let you get to the programmability of a graphics pipeline, but there hasn't been a single programming framework that lets you write code that can run parallel and can run portable across these different architecture types. And that was the original thinking behind the need for a new standard. So the group thought pretty long and hard about how it was going to focus its efforts. The commercial objectives of OpenCL, the most obvious one, as we've already said, is to grow the market for parallel computing. All participants in the parallel computing industry, not just the hardware vendors, but we hope that OpenCL will create opportunities for middleware vendors, application vendors, tools vendors. Really the whole industry, we hope, can benefit. We want to create, in the Khronos way, we're focusing close to the silicon. We hope OpenCL can create a foundation layer for a parallel computing ecosystem. You'll find tools and other languages and applications building on top of this low-level interface into parallel silicon. We want developers to be able to easily write applications that tap into parallel compute in a broad range of devices, not just CPUs and GPUs, but cells and DSPs and other processors that people might invent. We want to support a wide diversity of applications. This isn't just for high-performance computing, big metal applications. We want this to be used in consumer applications and eventually even on mobile devices and mobile phones. And probably most importantly, we want this to be a framework that lets people write code that are portable across many systems from many different vendors. Again, not just high-end metal, but desktop systems and handheld systems. OpenCL 1.0 has been designed to ship quickly. You'll get an insight from the other speakers this afternoon when the first implementations are likely to ship. So OpenCL 1.0 has been designed to run on today's silicon, but OpenCL will also provide a peg in the ground as it evolves to encourage and enable the silicon vendors to adopt and invent new functionality to provide more functionality to the programming community. So the actual OpenCL working group, it's about 25 to 30 companies actively participate in the group, quite diverse participation. Again, OEM vendors, all of the key silicon vendors, middleware vendors, tools vendors. We've had many of the industry's experts participating in the working group. We've been fortunate in the amount of expertise that has been focused into OpenCL's design. The project was initially catalyzed by Apple, and Apple serves as specification editor, but we've had broad input from a wide range of industry participants, and so it truly is an industry standard built by the industry. A couple of things to put OpenCL into context. Kari from Nokia will talk a little bit more about this, but OpenCL already includes an embedded profile, which is designed to enable OpenCL to ship on embedded and mobile devices sooner than you might expect. Some of the data types and precision requirements are relaxed, but it's still going to be a very proficient parallel programming framework to enable a new class of applications to begin to appear in mobile and handheld devices. Again, OpenCL is not just for high-end computing applications. It's intended to create new market opportunities across the range of devices and markets. The other thing that we might mention a little more later on is OpenCL has been designed to work closely with OpenGL, which is the desktop 3D graphics standard. OpenCL and OpenGL have been designed to share memory resources very efficiently, and applications can use which of the APIs best suits their particular part of an application. So you can use OpenCL for compute, OpenGL for graphics, to begin to build very rich visual computing applications. OpenCL and OpenGL enable the compute and graphics resources in a system to be very flexibly and efficiently utilized. So if you look at OpenCL in the context of all of the projects that Khronos is creating, OpenCL is at the center of an API ecosystem that now has taken hundreds of man-years to create. On the desktop side, OpenCL interoperates with OpenGL. Collada is an open standard 3D asset interchange format, so you're getting a good authoring and desktop and high-end system visual computing capability. Khronos has put a lot of effort into multiple mobile standards. OpenGL ES is a sibling API to OpenGL for 3D on mobile phones, OpenMax for audio and video media, OpenSL for audio, OpenVG for vector graphics, and some umbrella APIs that define how all these APIs work together on a complete platform. Increasingly, all these kinds of markets and devices that we've been working on at Khronos are going to need parallel compute capability, and OpenCL will be the foundation stone around which that parallel compute capability is built. So how is OpenCL coming together? What's the timeline that we're on? Apple initially proposed OpenCL in June 2008. We had an intense 6 months where we refined and made that specification into a true open standard. It was publicly released in December 2008, just 6 months. I think is a world record for an open standards organization. I think that's testament to the commercial need that all of the members felt. They just knew that if we got this work done quickly, we could all benefit commercially. There's a real motivation to get it done fast. Khronos released the conformance tests, which are quite exhaustive, in May 2009, and we're expecting multiple implementations to begin to ship in the second half of this year, and the vendors will give you some insight into that. Apple has publicly announced that Mac OS X Snow Leopard will ship with OpenCL integrated into the OS. We're figuring out right now when we should release OpenCL 1.1. We want to keep forward momentum, but we don't want to move too fast. We want to get developer feedback. So we are definitely open to developer feedback as the first implementations begin to ship. And we will feed that feedback into OpenCL 1.1 in the first half of next year. Khronos has some resources up there on the web. If you're using a particular vendor's OpenCL, of course, you'll get more resources from that vendor as well. But on the Khronos website, there's the registry, which is the home of the spec. There's the reference card, which hopefully everyone has a copy of today. There's a PDF version up on the website. There are developer forums on the Khronos website, so if you're using OpenCL or implementing OpenCL and you want to give us feedback, please go to the forums and tell us honestly what your feedback is. We do closely follow those forums, and that's a useful feedback channel from the industry. If you're implementing OpenCL, Khronos has quite an extensive conformance test suite. Tests both precision and functionality. You can get access to the source code for a small fee. If you upload your results, which are peer reviewed by the other working group members, and you pass the tests, you get a license to use the OpenCL trademark in your implementations. So for OpenCL, software developers are going to find a good API for portable parallel programming. It's a ecosystem foundation. We hope there's going to be a rich diversity of tools and languages and applications built on top of OpenCL. For silicon vendors and OEMs, we'll find a software momentum that lets us ship more hardware. And most importantly, of course, the whole point of this is that end users begin to benefit from better applications that make better use of parallel computing where it's available. So if you're interested in OpenCL and you want to get involved and have a voice in how OpenCL evolves, please feel free to join Khronos. You would be very welcome. Thanks.
Thank you, Neil. We have Mike Houston going to talk about OpenCL at AMD. So Mike is an architect at AMD. He's working on architecture and programming models for parallel architectures. He has a PhD from Stanford and focused there on programming models, algorithms for parallel architectures, including GPUs and multi-core and clusters. So welcome, Mike.
Thank you. So Afi's sort of giving you a solid overview of OpenCL, so I'm actually just going to jump right into what our device looks like in OpenCL. So I'm going to talk a little bit about what our current shipping architecture is and what it looks like into OpenCL. Talk a little bit about how to think about sort of what we call spreadsheet performance analysis at a high level, sort of how you figure out based on the code you've written what your performance is going to look like, tips and tricks, and then I'll run a quick demo of our implementation running. So I didn't get super deep into it, but when you query a device and you sort of report back a bunch of things, you can query things like how many processing elements does my chip have, how many compute units, how many total devices are in the system, and here's sort of a pictorial diagram of what that looks like. So, for example, let's say you have a Radeon 4870, so that's our current highest end consumer GPU. Well, we report 10 compute units because we have 10 SIMD arrays in our chip. Each one of those is comprised of a 64-element wide execution context. And these represent our processing elements. So if you actually dig into what the architecture looks like as a whole, and let's sort of dig into what these cores actually look like, these compute units, these 10 SIMDs. Well, we have 16 processing cores per SIMD, so big fat ALUs. And we process 64 work items over 4 cycles, so 16 times 4. So we have a branch granularity or an execution width that's effectively 64 wide. Now, each of these 16 processing cores has 5 ALUs in it, so we are a 5-wide VLIW machine down to its core. And so if you sort of break it all out, here's sort of what the chip looks like. It's a giant C of ALUs. Effectively, if you actually look at a die shot of this, which you can find online, I wasn't allowed to bring a wafer in today to pass around because it's $5,000 worth of sand. But if you actually look at the chip, you'll actually see there's a big block, and it's just a ton of ALUs. Then you see texture units on the side, so where texture caches are, and then sort of surrounding fixed function logic. Fundamentally, that's what the chip is and what the chip looks like. So let's talk a little bit about one of the most important things when dealing with GPUs. So GPUs, compared to CPU, have very small caches. So we only have tens of kilobytes effective cache sort of per compute unit, where GPUs are now approaching megabytes worth of cache. So instead of using cache, we have very, very large register files, which allows us to put a tremendous amount of threads in flight. So we gain latency hiding and efficiency on our engines by basically massively overcommitting the chip with the amount of active threads in flight at any one time. So ideally, you're going to launch way more work than you have available ALUs to actually get latency hiding mechanisms to work and allow us to efficiently schedule for both execution as well as memory access patterns. The register files in our chip are dynamically partitioned amongst active wavefronts. So we don't have a fixed number of registers that you can have per thread. We have a huge register file, and depending on what your resources are, we divide the register file up dynamically by the amount of threads executing in the chip. So for example, you can write your code similar to running a 64-bit mode on an x86 and use 16 float 4 registers per thread, or I can give you 128 registers per thread. The more registers you use, it means the less things you have in flight, which means the less effective latency hiding you have. So there's trade-offs in how you use the chip. And the chip is incredibly dynamic. As soon as you hit a long latency operation, say to calculate a branch or to do a memory access, basically your thread is put to sleep and the next thread on the run queue is now made active. So it's your good old traditional multi-threading machine. If you've ever read the Terra MTA papers, this will actually look pretty similar, except we're a massive vector machine as well as a threaded machine. So if you think about how something's going to process as I execute through, so waves are our term for the SIMD execution width. So as you start calculating on the first wave and you do a memory load, so instead of stalling and waiting, you immediately switch to the next wave. And this is going to continue. And hopefully if I'm able to fit 4 waves on my machine, I've done enough computation, I've done enough ALU load that I've now covered all the latency so I can come back to executing wave 1. And I've actually kept the ALUs busy the entire time. Right? So we can 0-cycle switch between threads on our architecture. So as long as I have math to do, I can cover all the memory latency in the system, as well as branch penalties and anything else. So more math is good. One of the things to remember in general on GPUs is, although this sounds strange when I have to explain this to undergrad programmers, sometimes you're better off recomputing a value than trying to store it and read it back, or even pull it out of a table. It's cheaper to actually do the math than to pull bits across the bus. So as you dig into sort of what we call spreadsheet analysis, figuring out what your bottlenecks are going to be. So some of this is in graphics speak because, well, this is a graphics chip fundamentally. But your first order bottlenecks are either ALU, texture access, so in OpenCL speak that would be an image read, or memory access. So your time spent in the kernel is the max of these 3 things. And if you want to calculate sort of what the ALU rate is on this thing, or how many ALU operations you have to do, well, it's the number of elements, so your global size in OpenCL speak, the number of ALU instructions, and by this we mean VLIW instructions. If you get perfect packing, you can divide your scalar ops by 5 on our chip. You will not always get perfect packing. The number of SIMDs, the cores per SIMD, and the engine clock. So if we step back and actually think a little bit at a higher level, and I'll get to sort of how many threads you have to put on our chip in a second to be efficient. But fundamentally, you want your workgroup size in our chips to be a multiple of 64. Why? Well, our wavefront size is a multiple of 64. That's our fundamental scheduling unit. So you want to maximize your resources. So if you use smaller workgroups than this, you're going to be underutilized. The other thing is for branch coherence, 64 is your target. And you want 64 threads together all going the same way. Fundamentally, your best performance is going to be if everybody in the work group manages to go the same way. Then we have no stalls on branch divergence and rejoining. So fundamentally, to get through full latency hiding on our chip, we actually operate in pairs of wavefronts. So what that means is while we've essentially done the instruction decode on one wavefront and it's executing, we're getting the instruction decode on another. So at a minimum, you need 2 wavefronts per core to just get minimum latency hiding on our chip. So how many work items do I actually have to execute to even fill the chip? Well, we have 10 SIMDs. You need 2 waves per SIMD, 64 elements per wave. So at a minimum, you need 1,280 items. So Aaftab wasn't kidding when he said you need to have a lot of parallelism to run on a GPU. You need to launch a lot of stuff. If you launch just this many, however, this is the minimum global size to fill the chip. You get no latency hiding here. The suggestion for minimum amount of latency hiding is to double this, to put 4 waves per chip, like the diagram that I showed, which would be 2,560 elements. In practice, what we find is that we tell most developers to shoot for 8,000 is the number of work items you want to put in flight. Let's talk a little bit more about registry usage. So recall that GPUs high latency by switching between large numbers of wavefronts. And your register usage in your kernel defines the maximum number of wavefronts you're going to put in flight. The more wavefronts you have, the better latency hiding. The fewer wavefronts you have, the worse latency hiding. There's an interesting caveat there, though, where if you manage to actually have lots and lots of live registers, it turns out that you probably have a tremendous amount of math that you're executing. It'll also be very difficult to get that many live registers, which means you probably have a lot of latency hiding already built into your kernel, right? You have long runs of math. So you do some loads, a tremendous amount of math, you do some other loads. As long as you can hide all of the memory latency with your math operations, how many cycles you're spending in math, you're going to be in good shape. So general advice for coding, looking at what the API provides. So similar to a CPU, our cores I/O systems are really designed to run efficiently when you're doing 128-bit fetches and stores. So that would be int4 and float4 in OpenCL. For VLIW architecture, this also takes a lot of strain off the compiler, trying to be clever, packing in to VLIW. Right? If you already give us 4 out of the 5, we can do pretty good underneath you, it turns out. You want to consider the access pattern. So Afi mentioned this sort of in performance tips. You want to try to get as linear access patterns as you can in your work group. This allows really efficient coalescing into the memory system. Remember that modern GPUs run pretty exotic memory systems compared to what's on your average CPU. So we're running very wide, very high-speed memory interfaces, which means we prefer very wide data access patterns. So we're going to issue 16 loads and stores per clock per core. Ideally, you want all those to be linear, so we're hitting the bank interleaves across DDR5 as efficiently as possible. So on AMD GPUs, we have very large register files compared to some other architectures. And so one of the ideas is to literally perform more work by using a register file. So a simple example would be take your scalar loop, naively unroll it by 4. So you've now bloated your effective register usage up by 4. But you also have 4 times as much work in your kernel. And I have an example in a second. So let's talk about median filtering. This is just a baby example. It's easy to look up. There's an article on Wikipedia on median filter. It comes up commonly. What it's used for is to remove one-shot noise from images. It's a really simple algorithm, which is why it's here as an example. Basically, you load a small neighborhood of pixels. You sort the pixels. You hopefully use an efficient method in registers. You only have to sort the neighborhood, and then you output a median value. It's very simple. So here's all the code for the simple kernel, and this is naive implementation of the kernel. So the first thing you're going to do is you're going to grab what your index is and compute it. So you can get so this is a 2-dimensional launch. You can get your ID in each dimension and compute the final index you're going to use. You're going to handle the edge cases in this version. You're going to load the neighborhood. So notice I've done 9 loads to do this, right? So these are 9 32-bit loads, not the most efficient thing to do on pretty much any processor. I'm going to sort along the rows, and sort along the columns, and then sort along the resulting diagonal, and then output the median. It's as simple as it gets. Right? Find the median value and output it. So in this code, there's a couple auxiliary functions that we use. They're really simple. So we're going to convert an RGB value that's stored in a 32-bit int into a luminance value. A simple swap routine that's going to be used by the sort routine, and then the world's simplest sort routine, since we have to just sort. Notice there's branches in here. So it's something to actually look at when you're coding on a GPU. You may be better off manually predicating these or making sure your compiler is predicating these for you underneath. So what you want to do to optimize this thing is, well, you want to try to switch to reading 120-bit values. You want to compute more things. So instead of doing 1 output, let's do 4 outputs. And so a better algorithm for this is to load a bigger block of things. So let's load an 8x3 block via 628-bit loads, sort the pixel for each of those groups, and then output 4 median values via a single 128-bit write. So if you look at what we've done, the top basically looks the same. We're going to get a little fancier because we're doing 4 things at a time, so we're going to divide by 4. We're going to load the row above us, load the row that we're currently in, and load the row below us. So we've now done 628-bit loads as opposed to 9 32-bit loads. In practice, this is about the same speed on a modern CPU or GPU to load this much data versus the previous version. And then we're going to calculate 4 medians simultaneously. So we've done a lot more math, right? I didn't expand out all those functions here, but we've done a lot more math. And then we can actually, if we're careful, we can actually put this together so we can actually do a 128-bit store as well. So this is pretty efficient for what you can do on a modern CPU or GPU. So I'm going to show a demo. I'm actually going to show a different application that's more exciting than median filter. So it's an application that we've shown a few times now. So it's a simple particle simulation application. So I can do things like put some C4 in there, which everybody likes C4. Put a little metal tip on it, and spark it, and I can get it to explode. More interesting, perhaps, for some people is we can make a metal sphere, if I can draw on my trackpad, with a C4 core. Make sure that we can get to the C4. Put a little plutonium around it. Spark it. And eventually the pressure from the C4 will actually take the plutonium critical. No, this is not scientifically accurate. It's just good fun. So this is actually running on the CPU. It's running on my little laptop here. Obviously, there's not a Radeon 4800 in here, although I would like one. You can actually find a version of this where we show scaling from 1 to 24 cores using 4 Istanbul processors. You can find it on YouTube or off the AMD developer link. We actually get pretty good scaling. So, lost my clicker. So for the GPU, optimization is a balancing act. There's lots of things to consider. Register usage, number of wavefronts and flights. The biggest one for any architecture, and this is the one that we try to drive into people, or at least I do, is it's really important to pay attention to your arithmetic density. What is your ALU to memory access ratio? Sometimes it's going to be way better to recompute something than to try to load and store it. On architectures, you want a workgroup size that's a multiple of 64, and you want to put a lot of threads in flight. So you can actually go get our CPU implementation now. It's public. It's been submitted for conformance. It hasn't quite finished the conformance cycle just yet. So we submitted this during SIGGRAPH. So we have Windows 32, so XP, Vista, and Win 7 up, and Linux 32 and 64-bit up. Interestingly, the performance advice for a CPU isn't that dissimilar from a GPU. You want to use 128-bit types. So this maps well into SSE formats, right? When you do a float 4 addition, what do you know? We generate, the MMAdd PS function underneath. We also generate, since we know you're doing float 4s, we'll actually generate aligned load stores using the SSE unit. Use reasonably large workgroups. This actually helps L1, L2 cache locality. If you use local memory in our implementation, we do our best to map that into L1 and play around with a cache to try to keep it there for you. You want to do a lot of work per work item. Our CPU implementation is designed so that if you code for a GPU, you're going to get good performance on a CPU. So you don't want to run a workgroup of size 1 on your CPU. You want to run a workgroup size of 256, 512. That's how we've designed things. That also gives you really good locality if you're relying on sharing between a workgroup. So CPU and GPU really aren't all that different, and it turns out. So the implementation's up. You have to actually register to be an AMD developer now, but it's an instantaneous response. We are actually working on getting that removed so that anybody can just get this willy-nilly and do whatever they want. So we have a forum up. My suggestion is, since this is one of the public implementations that's out now and you don't have to have anything fancy to run this, it'll run on a pretty low-end laptop, is to grab the implementation, start playing with it, mainly so that we can get developer feedback as we head into newer specifications for OpenCL 1.1. What works here, what doesn't? What do we need to fix? All those sorts of things are things that we'd really like to know as we head into OpenCL 1.1. So that's it for me, and I'm way ahead of time.
Thank you, Mike. So next up is Tim Mattson from Intel. And Tim's a principal engineer at Intel. And he's a parallel programmer. And he's also a open ocean kayak instructor. So you can ask him about that. He's been working on parallel computing for quite a long time, starting back with the Caltech JPL Cosmic Cube, and worked on just about every kind of parallel system, including massively parallel, VLAW, SIMD, clusters, SNP, NUMA, and vector supercomputers. So, Tim.
Okay, thank you. Here's my clicker, right? All right, so can everyone hear me all right? Good. I have the enviable position of being the last speaker between you and your next infusion of caffeine. So I'll try and not run late and make sure I get over in time. So my title is OpenCL Heterogeneous Computing in the CPU. And that's very deliberate because really I'm not going to talk at any great length other than just a few slides that are Intel specific. Because my major concern is getting things as portable as possible, so you really enable an ecosystem that stretches across all the devices. Because only then will we have the software industries that really allow these many-core devices to really take off. So I'm going to talk about heterogeneous computing and OpenCL, which I'm pleased to see almost everyone else has been hitting on, so I don't need to spend long there. Then I'll talk about data parallelism in OpenCL, some different twists on it as you think about how this looks as you move on to the CPU. Then a few words on task parallelism, and because I'm in a research lab, I have to at least have one bullet that talks about the future, or I can't sell it to my management that I'm not just offloading the product groups. So I'm really, as I said, I'm pleased people have been touching on this, because to us it's very important to realize that what OpenCL is about is heterogeneous computing. And if you look at just the devices we have today, they're already quite heterogeneous. You have, one or two or more CPU sockets, each of which has some number of cores. You got a GPU. You may have other devices on there. And so it's already a quite heterogeneous device. And over time, I believe heterogeneity is going to get even more extreme as we start looking at specialized silicon and other types of processors in the platform. So heterogeneity is something we need to get used to and really embrace. And the goal should not be to offload the CPU. The goal should be to make optimum use of all the devices you have. But I think everyone said that now, so it's really good. All right, we're getting somewhere. So OpenCL is not just a GPU language. What I think of it as when I look at the history of programming models that are out there, and I've had the unpleasant distinguishing feature of having used probably more than most people. OpenCL is really an application programming interface to coordinate heterogeneous parallel computing. It's really a coordination environment. I mean, yeah, there's a language and there's libraries, but it's really about coordinating heterogeneous devices. And if you look at the literature, you'll find quite a bit of systems out there that look at coordination, but OpenCL is the only one that was really designed to really keep in mind bridging the CPU to GPU gap. So you see this when you look at how each device has an asynchronous work queue and how you have this actually very flexible and powerful model with the event handles from different computations that you can coordinate in various flexible ways. It's actually a very flexible environment for coordinating functions. And then we have this marvelous little native function definition. So you can even drop in and start coordinating execution to non-OpenCL computations. For example, I'm looking forward to being able to, from within an OpenCL kernel, launch off a task that's going to turn around and call one of our parallel math libraries. So I think that native function interface is going to have a lot of use as we look at how to integrate the legacy software in with OpenCL. So it's interesting as you start thinking about how OpenCL looks when you move on to a CPU-like device. And as we see it, there's two different styles of exploiting the data parallelism that we think in terms of. We're not necessarily in love with these names, explicit SIMD, implicit SIMD, but the concept is what we're really pushing at here. In the explicit SIMD, what we call an explicit SIMD style of data parallelism, the kernel defines just a single stream of instructions, and you extract extra parallelism by taking into account the explicit width of the vector. So you match the vector width to what the hardware needs, and you tune that to get the performance you need. So you're very, very explicitly programming to the width of your vector units. Whereas in implicit SIMD parallelism, you're really embracing the style that the shader languages use. And what I mean here is you're going to create large numbers of these kernels as scalar programs, and you're going to be mapping these scalar executions onto the lanes of the SIMD units. So the vector types are tuned to what the algorithm requires, not to what the hardware stipulates. And that's really the big difference between the explicit and the implicit SIMD. And what makes things so interesting is when you look at the CPU, you can build an excellent argument for one or both of those. And so in particular, when we look at Intel processors, right now you can very effectively use the explicit SIMD. The programmer just chooses the vector type, and you may use a compiler hint to help guide the compiler to pick the best vector width. You also can use the implicit data parallel. And this is really nice because even inside of Intel with SSE, AVX, and Larrabee, we've got 4-wide, 8-wide, 16-wide platforms that we have to deal with. So it's quite a diversity even within one company's product lines. And then you can even, just to make things all the more interesting, when we look at how we're going to live with OpenCL and thrive with it in a CPU world, you can have hybrid mixtures of those. So for example, on the upcoming Larrabee, I could run this as 4-wide groups. So I could mix the explicit and the implicit. So there's a rich diversity, which from a research point of view is really exciting because there's lots of research questions to dig into. From a product point of view, it's probably very confusing. But, oh well, that's their problem, not mine. So, so here's an example of what I mean by explicit SIMD. And so in the explicit SIMD case, what you do is you have these loops in your original program, and you look at the vector width that you're going to be optimally finding will do the most for you on a particular platform. You're going to block those loops and use those explicit vector widths to get the performance. And you can see that here, and it's a trivial example. Boy, this is a really pathetic laser pointer. I hope you all can see it. So, oh, wow. I love green laser pointers. Oh, awesome. So, anyway, so here's the original simple little program, a simple loop. And what I mean by the explicit SIMD is I say, hey, I want to go 4-wide. I want to program this kernel so it will exploit a 4-wide SIMD. So I'm going to declare these arrays as float 4s. And then I'm going to change my loop so it goes instead of n over 4. And now it will take advantage of that SIMD unit very nicely. So you tune your code to the specific vector width of the platform. This works very well. So here's an example of a study we did with some implementation of OpenCL running on some dual-core system. And it was looking at a video contrast color optimization kernel. And we go through a number of steps here. So first off, we went through and we hand-tuned it and multi-threaded it and got this level of performance. And what the question was we were trying to see is how close to this hand-tuned performance could we get using OpenCL? Because the advantage is, of course, this hand-tuned approach is completely non-portable. You move it to another, I mean, I can't imagine why anyone would ever want to move to a different processor than an Intel processor. But if you did, it wouldn't work at all. But if you do it with OpenCL, you at least have that flexibility, should you want it, to move to another processor. So there's advantages to the software developer to having a portable interface to getting this tuned performance. So here's what we started with, and we used 1 work item per core. That's kind of a natural way to do things with this explicit SIMD approach. 1 work item per core, and we were running it, and we got this 20% of the peak performance. Then what we did is we did that trick I showed you on the previous slide, where you figure out for each data type how to get things to align just right and to fit with the vector width on the platform. So you blocked everything, blocked the loops, packed them into unsigned short 8s and short 16s. And that got us up an improvement of 40%, a pretty significant jump. Then in looking at that process, we discovered that there are ways you could better optimize how the indexing was being done to get the memory access patterns improved. Basically tuning the memory access patterns to the platform, but we were able to do it just by transformations within the OpenCL program, and we got a huge 186% jump. Not surprising, you optimize for data movement, you see big improvements in performance. Then we unrolled loops to try and get more work happening per memory access. And when we were done, we were within 5% of the hand-tuned SSE and multi-threaded case. But now we have a portable code that you could move to any platform supporting OpenCL. So I look at that as a software developer. When I'm not kayaking, I write software. I look at that as really cool. 95% with a portable implementation. I didn't have to open up the manual and look at all those SSE instructions, even though I love them. They're wonderful. Don't turn me in and tell people. I just love those instructions. I use them all the time. But the bad news is when I move to another platform, even another platform within the Intel universe, I have to go through and redo all those optimizations again if I want to get the performance. So I do not believe that this explicit approach is the right path to take in the long run. I think we need to think of a different approach. And I think what we need to think about is this implicit SIMD. So here's an example looking at a bilateral filter. And I'm not a graphics guy. To me, they're all different kinds of stencil algorithms over different data structures. But if you're really interested, you can go read more about this, and we give the reference in your notes. It's basically, I'm going to apply a Gaussian finite filter along an edge and slide it over an edge. And it's an edge-preserving filter. Now, my eyeballs don't read well enough to read that, so I kind of blow it up so you can actually see it. And what you have is this loop right here over the pixels of the image. And then you have these loops over the colors in the data type for each pixel, and then a whole bunch of loops that go over the finite width of that filter. So you got these tightly nested loops that are going in to establish this filter. So what we think you should do with the implicit SIMD is you get rid of those outer two loops by using the OpenCL approach with an ND range index set. Okay, so, and then now you've all heard that, so I don't have to go through and describe it, which is great. But the size of our index set is not the number of pixels, it's 4 times the number of pixels. So now I'm going to, basically coalesce those two outermost loops. So I'm creating a large, huge amount of work, 4 times the number of pixels in the image. And so now I'll be able to just have one layer of loop left, and I'll be able to leave it to the compiler to figure out how to map these onto the lanes of a SIMD unit. So my program kind of looks like this. This is just in words what I said. Notice there's no longer a loop over the pixels in the image. There's no longer the loops over the colors in the image. It's all just this one loop we're taking that into account with the OpenCL data parallel model. And you end up with something that looks like this. But we believe that this code here has the potential to not only be performing really well on our CPU, but it should work really well on a GPU. It should work really well on any of the platforms that support OpenCL. In other words, we believe that this style of implicit SIMD is going to be the more effective way to have portably performant code. And the one glitch in this, and when we first started talking about this, and the people working on this started telling me that this is really what they believed, that the compiler would just sort of figure out how to map things into the SIMD lanes, I just about barfed all over them. Because, I mean, I've been writing parallel program a long time, and I've had compiler people promise me magical compilers that could do great things just all the time, and they always fail. But what they came back and pointed out, and it took me a while to realize they're right, that what they're talking about of taking all these work items and mapping them onto the lanes of SIMD units, that's what the shader language people are doing already. So in other words, we're not talking about an unproven technology here. We're just talking about applying a particular known technique to how we process OpenCL. So it made me realize that I guess I don't need to throw up all over, and they might actually be able to pull it off. And this would indeed give me something that's more portably performant. So task parallelism in the CPU world, we're very interested in the task parallelism. And it does exist in OpenCL. And you can think of task parallelism as a way of breaking your job down into some asynchronous function calls. So I can do a computation y and say do x at some later date. And these tasks, if you have a good implementation of a system, they're set up to be very lightweight and they occur in user space. Now, here's why we believe this is so incredibly important in a language like OpenCL. As we've heard from the other talks, to really get OpenCL with that data parallel style to work, you need many, many thousands. You need tens of thousands of items to do, of work to do. Of course, in a graphics sense, that's a completely natural thing to expect, so it's a really great way to go. But the reality is, in the real world, you don't always have thousands of things to do. Sometimes you have just a modest number. So this is where the tasks are going to become very important. And so on a CPU, where you have a modest number of cores, it's actually a very natural fit. So there's an in-queue task capability, which would just allow you to set up your queues and then just throw out a sea of different tasks to execute concurrently. It's actually a very effective programming model. And I think I said much of the words on here that you benefit from this when you just don't have thousands of identical tasks. And when you do have thousands of identical tasks, you can go and use the data parallel sense. Now, this is really important for those of you. I see some of you out there who are old like me. In the early 90s, there was an explosion of these purely data parallel languages. HPF, the thinking machine folks were spinning off versions of their languages. And how many of them are in serious use today? The answer is something approaching 0. And the reason is you found when you started looking at a wide range of problems, even problems that appeared highly, highly, highly data parallel would always have a little bit that was task parallel. And it was actually these languages failed, I'm convinced, and I would love to argue with anyone who feels otherwise. These languages largely failed because it's really hard to take a task parallel algorithm and shoehorn it into a data parallel language. The other way around is real easy. You give me a task parallel language, I can drop data parallel into it, no problem. Now, that's why it's so important that in OpenCL, we took this into account from the beginning, and we created a language that had task parallel and data parallel coexisting side by side. And that's a very important feature of the language of OpenCL. I want to close with a little bit on the future direction. So building off of what I just said, we really see that in the future you're going to have applications as we start generalizing away from the GPU, away from just GPU, away from just graphics, and we really look at taking things that are from the whole traditional mix of parallel programming. As we move them onto these OpenCL platforms, you're going to have a complex mixture of serial parts, of data parallel parts, of task parallel parts, and they have to be able to mix and combine together in a single program. So we really believe in the future, and where programming models for these sort of heterogeneous platforms have to move is with something our marketing people call braided parallelism. Basically, the idea is you're composing data parallel and task parallel constructs in a single algorithm. And it's really clear when you look at the sorts of algorithms we're looking at and where computing is moving that this is going to be the way parallel computing will look in the future. And I'm really hoping that you can do some of this now in OpenCL, and I'm hoping as time goes on, OpenCL, I'm sure, will support this very well. If you ask what sort of platform is going to really work well with braided computing, this is where I think Larrabee is interesting to look at. And I'm not going to make this a large Larrabee commercial because, quite frankly, I'm in a research lab and I don't know much about Larrabee. But I know a little bit about Larrabee, and some of the stuff I know makes me really excited when you think of it in that context of that braided parallelism, of the ability to mix data parallel and task parallel. So Larrabee, you have some number of cores, and we have it on this wide ring bus. So, and this gives you a very fast access to other cores and memory and other devices on the chip. And notice that some of these devices on the chip are fixed function and texture logic. So it's a heterogeneous chip. It's not all the same. They're going to have different kinds of computing going on the same chip. So I think it really is indicative of where I see future chips going, of heterogeneous many-core chips. It is cache coherent. On the stops on the rings, you also have a L2 cache that is partitioned and distributed about the chip. So it's going to provide some very high aggregate bandwidth, and it's going to allow very rich sharing of data between the cores. I mean, it's a shared address space that we're moving into a many-core graphics-like processor. The core itself in Larrabee is very interesting. You've got your ring stop. You've got this shared L2 cache and L1 caches. Then you have a branch here as you have scalar registers and vector registers, but then you have a scalar unit and a vector unit. That scalar unit is a full x86, a full Intel architecture instruction set. It's an in-order instruction set because we're really designing, like pretty much everyone, we're designing with power as a principal concern. And these in-order data sets are much, much lower power. So we have an in-order, low-power Intel architecture core for the scalar computing. And then we have a vector unit that can do 16 32-bit ops per clock. The execution pipelines are very short, so I think the compute latency is going to be really nice on this. And a lot of good prefetch instructions that we've thought about very carefully to keep those caches full and keep the chip running at very high speeds. So I'm very excited about Larrabee. Yes, it's yet another vector instruction set we're bringing out, and that's well, neither great or not great. I guess it depends if you're a software developer or not. But it allows us to create a vector set that is really tuned just to this architecture to get a lot of speed. And if you access it through OpenCL, you'll be able to write portable code for it anyway. So I'm really excited about Larrabee when it comes out. But more importantly, as I said a couple times, I believe, not looking at any company's roadmaps, not even looking at Intel's roadmaps, because they don't show those things to me, but I think over time, this is the future. This is where things are moving, where CPU-like devices are going to look more graphics-like, and graphics-like devices are going to look more CPU-like. And so as things evolve, I think we're going to see this meeting in the middle as everything's integrated together on silicon. And it's going to be a very interesting environment for the programmer. And frankly, it's why I got involved with OpenCL, because it's my job to think about the future of programming models. And I think at the lowest level, at least, as a low-level common target environment, OpenCL has pretty much exactly what we need for this future vision. So at any rate, oh, I don't want to skip that one. There we go. You know, OpenCL defines an environment for heterogeneous computing. I say that every single time I talk about OpenCL because I hear so many people say it's just a portable GPU language, and it's not. I love GPU programming, but what I really like is being able to have a single programming model that mixes the CPU and one or more GPUs. And to me, that's really cool. I think if we do some very careful experiments, which all of us are doing right now, and if we really get a handle on what's the right way to do portably performant code, I think we can get OpenCL to that point where you write one program and it runs with good performance as you move it from platform to platform. If we don't do those experiments and figure out how to do it right, we might lock ourselves into an environment where you have to go through and know the vector widths and tune the vector widths and do all of that by hand, which would be very painful. And then I think the future is clear. And I keep this in mind as I work with the folks in OpenCL group in Khronos. I think the future is mixing task parallel, mixing data parallel, having a mix in complex ways, so I can have tasks launching data parallels and data parallel kernels launching tasks. I think over time it's really going to move to this mixed braided environment. And that's where I see it moving eventually. So at any rate, that's all we can say. Thank you very much.
From Chris Lamb of Nvidia. Come on up, Chris. And if we could have the slides for Chris, please. So Chris manages GPU computing system software at Nvidia. He's responsible for various GPU computing initiatives, including OpenCL. He has a degree from University of Illinois at Urbana-Champaign and was also an architect at the game physics startup Aegea, which develops the PhysX game physics code, which you can see out in the lobby. Thanks.
Thanks, John. So I'm going to talk today about what OpenCL looks like on NVIDIA's GPUs. Quick outline of what I'm going to talk about. First, I'm going to go briefly over the mapping of the OpenCL model onto NVIDIA's GPUs, how we see that playing out. Quickly go over some of the best practices that we talk to developers about to help them navigate the choices that you would have to make when mapping software onto OpenCL. There are a number of ways some of the other speakers have alluded to exposing parallelism in OpenCL, and we're going to go through a few of the guidelines that we give developers. And then some quick demos of both an application running on OpenCL today on NVIDIA hardware, as well as some of our developer tools that will be available to help you optimize your code. So OpenCL on NVIDIA's GPUs is actually a great match. There's a direct correlation between the execution model in OpenCL and our hardware, between the memory model in our hardware, and the synchronization model in our hardware. The implementation we have today of OpenCL is based on a mature GPU computing infrastructure that we've developed over several years now. Just like all of our other computing environments rest on this infrastructure and the PTX ISA, so does OpenCL on NVIDIA GPUs, compiles down to the exact same PTX ISA that our other GPU computing environments use. All of the profiling signals, instrumentation, the infrastructure for debugging are all available and have been developed using other GPU computing environments, and they're being translated as we speak, moved over to support OpenCL as well. Drivers and a full SDK for developers have been available after a quick registration on our developer website since this past May. They're all conformant as of right now, so if you want to try out any of the things you've heard about here today, go to our website, fill out the form, and you'll get access very quickly. It's available to all professional developers and researchers, so go nuts. It's also supported on a huge number of CUDA-enabled GPUs that are already out there in the marketplace. I know my laptop that I have at home supports CUDA, so I know I can program OpenCL on it. It's very likely if you've bought a laptop with an NVIDIA GPU in it in the recent past, it supports OpenCL as well. So here's a quick overview of our top-of-the-line 10 series architecture today. It's got 240 streaming processors. These are cores that execute hardware threads. These are organized into 30 streaming multiprocessors, each of which contain 8 of the threaded streaming processors, 2 special function units, 1 double precision unit, and a shared memory, which maps directly onto OpenCL's local memory. So in terms of the execution model, work items in OpenCL are executed by streaming processors. They're mapped directly onto hardware-managed threads that are scheduled at cycle granularity by the hardware. Work groups from OpenCL are executed on a multiprocessor. Several concurrent work groups can actually reside on the same multiprocessor, so you actually get another level of hardware scheduling and concurrency there. And then finally, a kernel with its ND ranged is launched across the entire device, with many work groups running concurrently, load balanced dynamically as they execute and finish, again by hardware. There's another direct correspondence with the memory hierarchy that's present in OpenCL, where each hardware thread has a dedicated private memory for its stack. Each multiprocessor, corresponding to a work group, has dedicated storage for local memory and constant caches, and therefore allowing the very high speed, high bandwidth communication through local memory. All work groups on the device can access the global memory, and atomic operations actually allow very powerful forms of global communication and really rich data structures to be used when computing across the entire device. It's a pretty important feature, we think. Synchronization. The OpenCL execution model actually puts some fairly strict bounds on what work items can synchronize with each other. We've implemented these synchronization constructs natively in our hardware. The independent atomic operations and memory system control of a single work item is reflected directly in the ISA. There's the ability to write collective and atomic operations in a very familiar style, a very familiar scalar C style in a single thread. Single instruction fast barrier support directly in hardware to implement the workgroup barrier function in OpenCL. And collective operations in OpenCL that leverage the entire workgroup's resources. Finally, at the highest level, we have direct hardware support for scheduling the commands in a command queue, like the ND range grids that execute a kernel. There's actually direct hardware support for scheduling the command queues that OpenCL exposes and resolving the dependencies that are set up by a programmer through CL events. So given that we've got a really great mapping onto OpenCL's different models for execution, there are some tips and tricks that you would want to use when mapping an application onto NVIDIA's hardware. A key concept here is that NVIDIA's hardware is fundamentally, as a previous speaker mentioned, implicit SIMD machine. It's a scalar architecture when looking at a single work item. That means that using the vector types that are most appropriate for the algorithm rather than thinking about vector types as being used for the machine. And in general, you want more work items rather than large vectors per work item because this exposes the maximum amount of independent parallelism to the hardware schedulers that are responsible for ensuring great throughput. Another thing that's very important, as others have mentioned, is this overlapping of memory accesses with hardware computation. If you think about the deep simultaneous multi-threading that's happening in the hardware threads executing on a single streaming processor, you want to give it the ability to overlap loads and stores as well as arithmetic computation on a single processor using its multi-threaded scheduler. And so having distinct phases and thinking about that when you're programming your single thread of work really makes a big difference, as it does on a lot of other architectures as well. You also want to focus on trying to maximize the number of concurrent work items that you have executing in your work group. NVIDIA's architecture, local memory is a huge factor in performance. It's hundreds of times faster than global memory in terms of bandwidth, and it's much lower latency as well. And critically, work items can cooperate via local memory. This is where the fine-grained synchronization of OpenCL comes into play. And you have this barrier built in the language that when you only use the CL local mem fence, you get this really tight, low latency synchronization on coordinating work items in a work group that are sharing memory in the local memory. You can also use it to directly manage locality, even if you don't, even if you aren't interested in using it to share work or synchronize. You can actually use it to stage data, tile data, these sorts of optimizations that allow you to explicitly manage locality as a programmer and take advantage of that huge bandwidth increase. So optimizing memory access is another of the really important key factors when thinking about NVIDIA's GPU architectures. Access locality of global memory is really important because of the high-speed, wide bit width buses that are used to global memory. In our latest architectures, we actually have hardware coalescing of accesses within a 128-byte memory block, which for a lot of algorithms gets you pretty much a lot of the way towards your maximum peak memory bandwidth throughput without having to think too hard about optimizing for specific, making it perfectly sequential across a work group or something like that. Generally, you get pretty good performance even with a very small amount of tuning or even no tuning at all. Optimizing for spatial locality of access in cached texture memory. So this is specifically for image processing. When you're thinking about image processing algorithms, image reads may benefit from processing in 2D blocks. And so when you think about how you map your execution space, how your work items in your grid map, are they 1D, are they 2D, are they 3D? Thinking about how that maps to something like a 2D optimized texture cache can yield great benefits for algorithms that use image types. Another important feature of OpenCL is that it lets the runtime optimize memory allocation. So here, there's a bit field that's passed into the memory allocation routines that allows you to say, hey, alloc this pointer, and it may be even in host memory, accessed over a bus by the GPU, but if you let the runtime allocate that memory for you, it'll be accessed in the most performant way possible. You can still get access to this memory both on the CPU and the GPU using the OpenCL API to map that memory back and forth. But if you use that particular flag, you get the most optimal performance from the device that you can. Another really important thing to think about for a device that may be on the other side of a relatively long latency bus is how you overlap the transfer of data and compute. So OpenCL has a really great API for controlling this. Even if you have separate command queues and a device that doesn't support out-of-order execution, commands in separate command queues within a single context can always overlap each other. So you can use this to overlap transfer and compute, and generally best when the time is balanced, but it's something that you can do on basically any OpenCL implementation. It's obviously most useful when data has high reuse, so that you make sure that you amortize the cost as best as possible. Another interesting option is to directly pass host allocated memory into the kernel. I think actually the last bullet point applied to this topic, that when you pass host allocated memory, this is memory that's probably in system memory, and you make that accessible over the bus by the device, you can actually get a net increase in available bandwidth because you're actually adding the small amount of bandwidth for the bus to the aggregate bandwidth of the device's onboard memory. And if you have a high reuse, you definitely want to move it to the device memory. But if you have low reuse, one-time use data, typically you're going to be hurt more by the latency of the transfer than by the actual bandwidth. And so in that case, it makes sense to actually leave the data in host allocated memory, transferring it just as you would accessing it by a pointer and transferring it to the device for one-time use. There you pay the lowest latency possible because you don't stage it to the device. And it's really great because it uses the GPU's already built-in multi-threading capability to hide direct access to CPU memory, which has a long latency. So you have a lot of hardware threads running. They hide that latency really well. It's very important to use parallelism efficiently. So this is thinking about partitioning computation to keep the GPU multiprocessor equally busy, which means many work items, many work groups, typically a lot more work groups than you have compute units reported for the device. And a general target that we give developers is about 256 to 512 work items per work group as a good target. Keeping resource usage low enough to support a lot of occupancy on the machine, that's a lot of hardware threads, is pretty important when you're developing code. So this again goes to the fact that, and on our GPUs, you don't have a fixed size register file per hardware thread. And so when you compile your application code, you can dial the register file. And that gives you this trade-off between how many hardware threads you want running concurrently versus how complex the code gets in a single thread. So there's a spreadsheet analysis tool that you can get on our developer site that will help you analyze this ahead of time while designing. Or if you already have code running, you can use our profiling tools to directly profile your code and see how well you're doing on a number of these metrics. OpenCL's math library is very rich. And as Afi mentioned, there's these three levels. For Nvidia hardware, the native and half math functions are actually very close to as accurate as the full precision by the specification, but can be many times faster. So in general, we recommend that people take a look at what kind of accuracy their algorithm can tolerate and if these native and half functions are actually accurate enough. A lot of GPUs these days have an FMAD unit that fuses a multiply and an add in a way that is not quite IEEE compliant, but actually provides a huge amount of performance and is not that far off in terms of accuracy for most applications. It's not on by default in OpenCL to keep compliance, which we think is very important. But if you're looking for the fastest running algorithm you can get on your NVIDIA GPU, definitely take a look at enabling that option. There's also a host of other optimizations that can happen in the compiler when you use the CL Fast Relax Math Compiler option, and generally ask people to take a look at that as well. So now on to some of the demos. So first I'll go over, I'm going to actually do this in a bit of a reversed order here. The first demo is actually going to be not the profiler, but then I'm going to show you how the profiler works by profiling the demo. So the OpenCL profiler facilitates analysis and allows you to basically get a lot of information from hardware counters that we have on the device. Number of bus transactions, branches, whether the branches are diverging or not, to give you an idea of actual instruction throughput, the effective parallelism you're achieving, the amount of memory bandwidth that you're using, the amount of instruction throughput, I think I said that you're using, and it gives you a visual representative of a lot of this data that can help you dig into your profiling information to figure out where your bottlenecks are and what the most profitable part of your algorithm to attack is. It requires no instrumentation of the source code, so you basically take it, you run it with a tool, and it gives you the information back. Here's a quick screenshot of one of the views with a time profile of OpenCL commands running from left to right. A number of uses that you can use this for is basically determining whether kernel performance is bound by instruction throughput or memory throughput, seeing whether you're limited by execution or transfer times, whether your application's time spent in the kernel on the GPU or is somehow being spent in overhead on the CPU trying to schedule it. And before I get to the demo, let me go a little bit over what the demo I'm going to show you is about. So the demo I'm going to show you is actually open ocean simulation in OpenCL, based on Jerry Tessendorf's paper, Simulating Ocean Water. It's a statistics simulation, so it's not physically accurate, but it looks really, really good. There's a wave distribution that's generated in the frequency domain. You basically perform an inverse FFT on this, do some Perlin noise at multiple frequencies at multiple levels to keep it from producing a repeating pattern. And it's widely used in CGI in movies in the 90s and games in the 2000s. For instance, Titanic, Waterworld used these. And in games recently, you've got Crysis and Resistance 2. If you notice between those two, the size of the grid that they use is actually pretty different. The cinematic ones use a really large grid. The ones for games use a really small grid. Turns out when you use a really small grid, it kind of looks crappy. There's a lot of high frequency detail that you don't get out of the simulation. So the great thing is that, skip over this. The great thing is that the simulation runs really, really well on GPUs. It's performance bound by an FFT computation, which maps really well to the GPU. And by running it on a GPU, you can actually perform these FFTs at such a performance, at such a rate that you can use the larger sized grids in real time, and it looks really good. And now we'll switch to that. So here's a GTX 285 running this simulation in OpenCL. The ocean surface is being computed in real time and then rendered on the exact same GPU. The rendering is being done via OpenGL here. So you can see, like when I get close to the surface here, there's this really high frequency detail that you get in the water that basically gets smoothed out if you have to use a coarser grid for the FFTs. So now what I'm going to do is I'm going to quit this, and I'm going to actually switch over to our profiling tool. And we're going to take a quick look at what it looks like. Here's a saved session, but I want to create a new one. So sometimes you can't get all the counters in a single pass. So I'm just going to just do this. And the profiling tool is actually going to launch the simulation, profile it, about 10 seconds, which might be a bit long. But it's very pretty, so we can all watch it. And then it's going to do another run. So here we have our second session. And we want to see where we spend our time. So here's where we spend our time. Majority of the time on the GPU is spent in this radix kernel. Looks like a FFT radix 8. The next most was some copying back and forth, and then another FFT kernel. If I want to see that time plot, this shows me over time what was actually happening on the GPU and the CPU in the runtime. Gives you a good idea of, over time, how is your program evolving? In any given time slice, what were the commands that were actually run on the GPU? Then I can go to this timeline view, which will actually show me concurrency or lack thereof. So here we actually have the different, you see a number of bars here. These are actually two different command queues that are being used by the application. One on the top, one in the middle, and in the bottom there's the aggregation of both. And so you can see in each frame here work that's being done in two different command queues. In this case, this is the copy, and here is the computation that's going on. And right now you can see here this is not so good. The compute and the copy aren't really overlapping. It may not be possible to do that in this case, but This tool would allow you to check on that and figure out, okay, am I getting the performance that I need? Am I getting the overlap that I'm looking for? So if you want to try this out, go to nvidia.com/OpenCL. There's a longer link on the bottom for our registered developer program where you can get access to our OpenCL runtime today. And I would also encourage anybody who's interested in GPU computing, interested in OpenCL, to take a look at NVIDIA's GPU Technology Conference that's coming up shortly in San Jose. There's a lot of really great content that's going to be discussed there, a lot of interesting things going on. And that's the end of my talk. Thank you.
Thank you, Chris. So now we have Eric Schenk from EA. And Eric is CTO of EA's Central Technology Group, and he steers the strategic direction of EA's Central Technology. He's been working there on networking protocols. He led the development of a cross-platform graphics library for EA games. And he's now focused on how to find ways to lower the long-term cost of developing games and how to write games that take advantage of highly concurrent hardware. Eric.
Thank you. So let me start out by telling you a bit about why, we're flipping ahead a little bit there, why EA cares about OpenCL. So as game developers, we're faced with a variety of platforms that have what amounts to heterogeneous computing environments. We've been building games on heterogeneous computing environments for a number of years now. So, of course, we're fairly excited by the possibilities of OpenCL for helping us with this problem. So it really helps us unify the programming for a bunch of devices that have different environments, and it provides a uniform interface for non-fixed platforms like PCs or Macs, where every user's got something different in their home environment. As well, it provides us with a concurrent programming model. So we get a command queue per device, which supports the dependencies across queues. This is very similar to the task programming model we already prefer. And it still lets us write data parallel and SIMD programs in a portable notation. Currently, we end up having to do this, as has been referred to before, in what amounts to assembly code or intrinsics if we're lucky. As well, it's a low-level programming model, and that's important to us from the point of view that while it will be really nice if the compilers help us do this stuff efficiently, we don't necessarily trust that. So how are we actually going to use OpenCL in games? So really high level. The first thing I'll say is that in a game context, we don't really have to try and speed everything up. What we're really more interested in doing is using the excess compute capacity that we get on any particular platform to add new features or more content. Some things are easy, other things are harder. I'll say a little bit more about that. So first of all, let me come back to this. What do we really need to speed up? So I'll just remind you of Amdahl's law. People often say to me, well, gee, you're not going to be able to speed up your whole game. Games are very complex. There's a whole bunch of code in there you really can't do anything with. And you know, Amdahl's law would cover that, and yeah, they're absolutely right. But the reality is we don't have to do that in the context of a game. The game's already running on the hardware we've got today. When we get more compute power, what we're more interested in doing is adding some more features or some more content. And there's usually hundreds or potentially thousands of things we can target at the new hardware that comes along in any particular given game. So we're going to try and move as many of those as are feasible, and we'll tune our efforts to what the hardware is actually capable of doing. And of course, our hope here is that OpenCL will make it easier to do the coding for this kind of thing. So what are some easy cases? So there's some obvious easy cases. You know, we already do rasterization and shading on graphics hardware. Obviously, that runs in parallel today. There's other things in rendering like visibility culling or procedural geometry that we got a pretty good handle on how to do. We just don't do it because the programming cost is too high right now. There's a lot of stuff in codec decompression and also compression around animation, audio, video codecs, and other types of compressed data. Generally, we're trying to get data into the hardware with as little memory bandwidth as we can, and that becomes an important problem. We also have animation blending in a lot of our games where characters are animated. That can be fairly easily parallelized. Audio mixing, some rigid body physics calculations, some collision calculations, and so forth. There's a fairly large number of cases that are relatively straightforward. Then there's a whole bunch of cases that are an awful lot harder. Artificial intelligence. Right now, we don't even try to tackle this for the most part because the programming it in intrinsics across multiple platforms would be a nightmare. But there's a lot of candidates there around pathfinding, search, pattern matching, and a whole bunch of other things. In the animation domain, once you move beyond simple blending of captured motion, there's higher level motion planning, maybe more detailed simulation of human behavior in large crowds. Things like that that we'd love to tackle, but right now we really just generally don't have the compute resources available for it. But it would make the worlds in the games that we write an awful lot richer. Similarly with physics, once you move beyond the simple stuff, you'd like to do the more complicated stuff. You'd like to deal with your broad phase collision, character-to-character interaction, maybe fluid dynamics. It'd be great to have a game where you walk down a hall and a rush of water comes down and washes you down the hall. That would be very hard to do today, but it would be nice if we could. The last one is a point that really ties to business models. Right now, we spend an awful lot of money building content. And if we could trade using processing power for using people power to do some of that work, either before we ship the game or actually in the game as it runs on your machine, we'd love to do that. So things that help us create assets like realistic landscapes, vegetation, architecture, whole cities, anything that helps us improve that would be a big bonus. So let me tell you a bit about what we've done so far. And obviously, it's a little early for us to tell you about games that we've shipped that used OpenCL extensively. As you've already heard today, implementations are just starting to become available. But we have been doing some feasibility experiments. So I'm going to tell you in particular in the rest of this talk about one particular experiment we did. And this takes a cloth simulation from an existing game that we've shipped. This is EA's Skate 2 game. The cloth simulation in the game was hand-tuned to run on PS3's cell processors and also to some extent on CPUs with a multi-core CPU. It took months and months to write and tune. It was an awful lot of work. So what we wanted to do is pull that out, port it to OpenCL, and see what kind of results we could get. So our goal here is to exercise OpenCL on something that approximates real code that we'd find in a game. Oh, sorry. Port the algorithms to OpenCL and leave intact as much of the original code and API as we can, because of course what we want to do in the context of game development is we've got a game that's already running. You want to take some algorithms and move them into OpenCL and disturb the rest of the code as little as you possibly can. So I'm going to show you this demo in a second, but what it actually does here is it's going to play back a recorded set of skeleton poses. It's going to skin the model to the pose. It's going to apply some cloth physics. It's a very simple physics model, very constrained. It's not full cloth or anything. It just looks OK. And then it's going to render it via OpenGL. So I'll just switch this over here and show you the character. So this guy's sitting here suspended in space right now. And if I tweak gravity, you can see his shirt move around a little bit. Now, this isn't a full cloth simulation, like I said. It's essentially a set of springs constrained to lie around the body, and depending on gravity, cloth will fall down or fall up, but it can only fall so far because the strings have a length constraint on them. Now, if I start this thing animating, it's running on the CPU right now, and you can't see them, but there's a whole bunch of other guys being computed at the same time because we want to maximize the work that's happening. And if I switch this over to running on the GPU now, you see it gets significantly faster. So that's the demo. It's not the most impressive thing from an artistic point of view. Again, this was more of an experiment to see how we could port these algorithms. I'm sure we're not saturating the GPU here. Again, that wasn't the goal. What we were looking at was how do we get the code running and simulate it in the most effective way and see what kind of speed ups we get over the CPU code that we already had, and how did that compare to what we'd hand done. I can't really tell you the comparison to what we've done by hand, but I will tell you what sort of results we got in comparison to the stuff that ran on the CPU. So what does the thing do here? It's a fairly simple piece of code in terms of the OpenCL task graph. There are 5 kernels that are going to get run in sequence. The first one will skin the model. Then we'll do a simple Verlet time-corrected integrator. We'll apply a distance constraint that keeps things close to the body. And then we're going to do a driver constraint that applies the forces of the animating body to the particles. And then we'll write it all back to the locations of the particles so that we can actually render the whole thing. So there's a fairly complicated data flow going on through all of this. And I'm not going to go through all of the details of the data flow in the talk here, but what's happening is these kernels are passing things back and forth through the memory buffers that were described earlier in the talk. And these are also tied back to the rendering system through an interop layer in OpenGL so that we can actually pass the vertices back and forth to the graphics subsystem. This is just done with OpenGL in this case. So what's actually happening then is the host will write things out to the pose on the CPU, will acquire the GL buffer for the OpenCL layer, and then OpenCL takes over, runs its 5 kernels, eventually writing things back into the vertex buffers. We release it for OpenGL to take over, and then we do the rendering. So we did 2 versions of each of these kernels. We did a scalar variant and a vector variant. And this was an experiment to see how the hardware and the implementations would perform with these different kinds of variants. Now, I'm not going to say this is representative of anybody in particular's OpenCL implementation today. It's not. This was the experiment that we did at the time. Expect these numbers to change as vendors release things over time and improve things over time. So in the case of a vectorized kernel, one of the things that we have to deal with and when we're optimizing is that quite often data is laid out for various reasons in a sort of array of structures sort of format where we've got XYZW data in float 4s in big structures that describe some particle or some other object. And that's not really that great for computation in a vector mode. You really want to have it in structure of arrays where you've got a float 4, say, or a float 16 that's got a whole bunch of X parameters. So one of the key things we use is a 4x4 transpose to convert between AOS and SOA. And it does exactly what you would expect. It takes things that are arranged as XYZW and turns it into XXXX, YYYY, ZZZ, WWWW. One more W. The other key thing that we do is we really want to avoid branching. And to avoid branching, we use the select statement that got mentioned briefly in one of the earlier talks, but we try to use this fairly extensively in the code. So rather than making a branch condition, you're going to calculate both sides of the branch, determine a select condition, and then the result will be selected by the select statement, and you don't have to do any branching in the hardware. So at a really high level, the vector version of the integrator, and I'll just talk about the integrator briefly as an example. It's not the most complicated of the kernels in this sample, but it's the easiest one to talk about. At a very high level, all that's really happening is we're going to load up 4 particle positions and their previous positions into some local registers. Then we're going to do a transpose from AOS order to SOA order so we can do an efficient calculation. We're going to pull up some flags that tell us whether or not the particles are allowed to move in this particular computation. Then we do a Verlet integration, which is just some fairly straightforward math. And then we do a select to determine which particle location is going to be picked, the original location or the newly integrated location. And then we transpose it back into AOS order and store the particle back. Now, in the handouts, there's more detail about this code, but in the interests of time, I won't go over it in any extreme detail. We already talked earlier about how work is divided up into work items that form work groups. So I won't go over this slide in too much detail, But in the case of this demo, all of the work is done as one-dimensional work groups. You can, of course, go up to 3, although if you need more dimensions, I suppose you can always reinterpret your one dimension in as many dimensions as you need. So when we did the initial tests, we ran it just on a CPU version of OpenCL. And in those cases, we got some pretty reasonable speedups. So the host numbers were sort of our reference unoptimized C implementation. And even just taking that code and translating it to OpenCL and running it on one core as a scalar task, we did get some speedups. Once we went to multiple cores, we got a pretty reasonable speedup. It's not quite linear going to 8 cores, but it's pretty good for the overall. And you can see that the skinning, for example, did very well. The distance integrator does very badly, and I'll come back to that one a little bit later because there's a reason it does badly that's algorithmic. And the vector code also does reasonably well, although it's not really that much better on CPUs than the scalar code. It's a little bit better, but not a lot better. Now, we got a little bit of a surprise when we ran this on GPUs initially. And again, this isn't necessarily representative of current implementations or any particular implementation. But initially, we found that on the GPU implementation we were working with, we had very bad performance. And there's a bunch of reasons for this. And most of them are algorithmic, and they point to some of the things you have to do to optimize. So the worst one is that the distance constraint algorithm modifies 2 particles at a time. And currently, we can't modify multiple particles simultaneously and get correct results. So the original algorithm ordered the data in groups of 8 particles that could work simultaneously in a work group. Now, that's a really tiny work group. You heard earlier people saying that work groups should be on the order of 512 to several thousand elements. This is obviously not going to perform very well on a GPU-type system. So we looked at the algorithm and reordered the constraints so that we got larger work groups. They're still not that good. They're actually still pretty bad, and it's limited by the algorithm that we chose. And obviously, this would be a case where you'd want to take a step back and say, maybe this is the wrong algorithm for this problem. But it really does point out the critical piece of information here to learn is that you really do have to be careful about the kind of algorithm that you're using, that you're going to actually be able to have very large work groups. If you can't have large work groups, you're not going to get very good performance on a GPU-style piece of hardware. So the other thing is that you want a large simultaneous data set, again, to make more work per task or to have larger work groups. Initially, our demo was running 1 character. An obvious thing we can do is run more characters. In a real game, you would process multiple characters as a single batch. So if you've got, say, a sports game where you've got 24, 25 people on the field, you're going to do all their clots simultaneously. For the demo, we just did a very simple replication of the geometry, and we saw a good performance increase on the GPUs. On CPUs, it doesn't really have much effect. The second important one is around optimizations to do with bandwidth. So it's been mentioned that memory access is crucial in bandwidth-limited kernels, and most of the kernels we look at we think will be memory bandwidth limited. And so quite often, if you're writing a vector algorithm, what you're going to want to do is get things into local memory before you start operating on them. And there's a nice primitive call that we can make in OpenCL to do that. And this is important for a couple of reasons, but the most important one is that burst reads from memory are what the hardware will coalesce on most of the GPU-type implementations, or if you're looking at something like a cell, if you're DMAing things explicitly, again, you're going to want to move things in a large block into local memory. So your algorithms end up getting divided up into this pattern where first all of the work items in your work group will cooperate to move things into local memory. Then they'll do something on all of that data in local memory after a barrier, and then they'll cooperate to copy it back into global memory. And you have to explicitly code for that, but it's actually not that bad because there's some built-in functions that let you do it. So when we do all of these things in our code, we got much better performance in our initial experiments. We got a factor of 83 speed up over our initial host implementation in the skinning, which was by far the best of them. You'll notice the distance integrator still does really badly at 1.73 times the original host speed. That's the one where we could really only do maybe 56 items in a work group, which is not that optimal, really. And overall, though, it got a reasonable amount of speed up, and we could see that we would get promising results that were similar to what we got when we hand optimized this on platforms earlier. So a bit of a summary then on what we learned in this process. First of all, performance tuning is essential. You can't just write the code, fire and forget, and expect that it's going to perform anywhere near the optimal. You do have to look at the profile, understand things about your algorithm, and do some optimization of your code. And the other thing, second thing is the performance characteristics aren't hidden by the abstraction layer. You have to understand the hardware that you're running on. So you can't ignore the characteristics of the hardware. At this point, what we expect to have to do is probably in a practical sort of situation with a game, we would write multiple variations of the kernels that are going to be running an algorithm, and we'll make a choice empirically that we're going to use at runtime for any particular kernel. The good thing is we don't expect to have to write that many variations, and over time we expect the number of variations you need to write to get smaller, and hopefully we get to the point where we really only have to write one variation. But even if we only have to write 3, and I have no idea why that clicked because I didn't even have it in my hand, even if we only have to write 2 or 3, that's an improvement where we're dealing with a world where we've got dozens of platforms potentially that we have to ship on. So that's the end of my presentation.
Thank you, Eric. So now we get to hear from Kari Pulli. Kari's a research fellow and member of the CEO Technology Council at Nokia Research Center in Palo Alto. So he's been working on parallel computer graphics since the days of transputers, and also was here at the Stanford Graphics Lab a few years ago. And at Nokia, he's been working on research and technology of mobile graphics and imaging, and has worked on several Khronos standards.
Okay, thanks. So hello, everybody. I'm presenting part of the work it was done by a research team in Oulu in Finland. And since I'm kind of a little bit closer, live about 1 mile away, I got the chance to come and present the results to you. Neil showed already this slide. OpenCL has this embedded profile. It's really a subset of the kind of full specification, and it's kind of different choice than what was done with OpenGL. OpenGL ES, kind of the embedded solution, is really a different API for that. The reasons why we did that in Khronos a while ago was that OpenGL was not then yet part of Khronos, and there was too much kind of legacy things there to be able to make same kind of profiles. But in OpenCL, we were able to design the mobile version at the same time as the full version. There are some pieces that are optional or missing on the mobile version, but mostly it just relaxes the requirements of kind of minimum required buffer sizes and so forth, and also the accuracy of the floating point operations. Here's one of the applications that hopefully OpenCL could be used to accelerate some of the other APIs of Khronos family. Can be already used to process images and render them on the display. And now we could do a little bit more kind of processing that's hardware accelerated. The main differences are listed here. The differences are quite small. You can write the code so that it runs on both profiles. If you write something so that it runs on mobile profile, it will run also on the full profile. There are two ways that you can handle this in your code. There's macros that at the compile time allow you to specialize your code for the embedded profile. And you can also query capabilities in runtime. Other things that are optional is the online compiler. It's not required that you can compile the kernels on device. There are no 64-bit integers, and there are these reduced requirements for constant buffers, object allocation, constant argument count, and local memory. Images are also optional, and when they are provided, images kind of as a data type. When they are provided, they only need to support what OpenGL ES 2.0 hardware supports for texture mapping. You can also use any extensions that you might have for the full profile on the mobile profile. But floating point numbers, first of all, the infinities and not number values. You don't have to do everything that IEEE spec requires. You can make a simpler version of your floating point hardware that saves on silicon area and power consumption. Also, accuracy requirements are relaxed. For example, division can be a little bit more inaccurate than for the full profile, and exponential logarithm operations as well. Also, when you do the float addition, subtraction, multiplication, MAD, they can be rounded down to 0 if they are very small, and denormalized half floats can be flushed to 0. About image support, which I said is an optional feature. Here are the requirements. It's basically the same what ES 2.0 hardware can do. So for writing out, you have to have at least one image if you want to support that, but for reading in, you can use 8 samplers or from 8 images. The images have to be addressable for at least 2 kilo, 2084 pixels on both directions. But the third direction, 3D, that would be optional. 3D images are typically not supported. They would require too much memory. The samplers for floating point images are simplified. Only point sampling is supported. So some of the benefits, actually most of the benefits are quite similar for the mobile profile as has been already discussed. It's really the portability of the code, and but this might be even more important on the mobile side than on desktop, because the variability of hardware is higher and changes faster. The APIs that are provided for application developers, they are typically at the level of, for example, Khronos standards, but what kind of DSPs you might have underneath, they vary from device and family of devices to another. And every time you make a change, you have to rewrite most of the code. OpenCL hopefully reduces this rewrite of the code. So write an application that conforms to the spec, and it will run also on future hardware. The heterogeneous multiprocessing can be also maybe more important on mobiles than on desktop. On desktop, you often have this kind of imbalance of processing power. Your GPU might really be 100 times faster than the CPU. And then you don't really need to do heterogeneous multiprocessing. You just shuffle off everything to the GPU. On mobile devices, the different units are more balanced. There's not really room, at least power-wise and silicon area-wise, to have this parts of the processing blocks that are much faster than the others. And, but then you typically have quite a lot of different kinds of processing elements available. So for example, on OMAP 4, you might have a couple of ARM CPUs, then an image signal processor, graphics processing unit, and DSPs for video and voice and so forth. So here's one use case that we use to do some profiling and to learn a little bit more. So we have implemented a kind of research version of OpenCL that allows us to better understand the spec and better contribute to the standard and do the requirements for hardware providers. The algorithm in this case is fairly simple. It's projecting an image to a spherical surface, as you might need, for example, when you create panoramic images, when you merge several images into one. So first there's this adjust geometry part, and then do Gaussian blur, and then adjust the colors so that the colors of the neighboring images might match better. You could implement these as 3 different kernels, but for these tests we implemented it as a single kernel that does all the steps, kind of makes the measurements more accurate. And the hardware that we used was TI OMAP 3 that has a CPU that runs at 550 megahertz and a GPU that runs on at 110 megahertz. 3 measurements, CPU alone, GPU alone, and combined. And we measured both performance and power. Here's the kernel. There's the definition part and the input arguments and output arguments. There's the input image and output image. And here would be the core. Define some variables. Here's a texture sampler and a couple of these vector data types. And we get the index for the current pixel using these ID getters. The first step is to adjust the geometry. It's basically just to recalculate where to sample the image. The second step is to do a simple 3x3 Gaussian blur. So we kind of calculate these offsets here and do 9 texture fetches and multiply them with appropriate coefficients. And the final step is just to adjust the color and clamp and write the output image. So some considerations when we compare GPU and CPU. Well, as I said, image 2D, this kind of optional type. And it's something that matches really nicely to GPUs. But if we try to emulate this on CPU, that's not very efficient. With CPU, we can use these memory buffers. They kind of match better what the CPUs can do. So in fact, we implemented 2 versions of this kernel. One for the GPU, it uses the image 2D, and CPU it uses the memory buffers. Here are some of the measurement results. If we just look, so 100 frames, 3 megapixel images. And if we just look at the processing times, we find out that for this task, this hardware, the GPU was 3.5 times faster than the CPU. The processing time per image for GPU was 2.4 seconds and about 2/3, so it was the real computation, and about 1/3 was just the overhead of transferring the data. And here are some reasons why in this measurement the GPU was faster. Well, the GPU matches OpenCL model better, but it's also, and it has these fast vector floats that are missing from ARM Cortex. However, it's probably also that because this kind of first version of research implementation of OpenCL, CPU part was not as optimized as it could be. So the neon instruction set was not used very well. And the algorithm was very floating point heavy. We have done some other measurements where we first converted the algorithm to fixed point when in some cases the CPU was even faster than GPU then. So then we tried using both of them together. You would expect that it would be faster, but in fact it was slower to do both of them together than to do GPU alone, and this was kind of surprising. And here you can see the red means that there's real processing going on, and black means idling. And well, you wouldn't expect and hope to get something like this, so let's analyze what's going on. Well, there's more overhead now for data transfer because you have to synchronize two processors. The GPU execution time remained the same as before, but there's more overhead for the data transfer. So really here's the problem, is that the data transfer overhead is doubled. And whenever you transfer data, CPU is fully kind of utilized. It's not idling. So when CPU is moving data or processing it and there's no data for GPU, it just needs to idle there. So scheduling is not easy. We could, if we kind of knew better what's going on and schedule better, get speed improvement by using both of them at the same time. If we had 84 frames using GPU, then we would kind of be 20% faster. And but then all of this depends so much on the implementation and the algorithm. So with the same implementation, if the kernel was doing more processing, everything could be different. And if the CPU happens to be faster than GPU, then you might just do all the processing on CPU rather than waste any time to transfer the data. Here's one topic that was less discussed by the previous talkers, energy measurements. This often is even more important than pure performance on mobile devices. Everything has to be run on batteries. So we did some measurements again. The input voltage was 3.8 volts, and there was some idle current that was subtracted. Now the difference between CPU and GPU is quite large. So GPU only used about 14% of the energy of the CPU. And if we somehow would be able to transfer the data more efficiently, the processing part is only 7%. Now we get something more than you would kind of expect beforehand. So if we know this, the GPU is most energy efficient, the CPU is least so, and then combination is somewhere in the middle. Again, some of the analysis, GPU is better match for OpenCL. Everything, all the execution units are busy. CPU suffers from poor ALU utilization. And then there's the clock speed differences. So typically, if you have high parallelism with low frequency, like in the case with the GPUs, that's better for power than low parallelism with high frequency, the CPU case. So summary, there is a mobile version of the spec. It's really just a subset, so it's fully compatible with the full spec. The promise is really easier programming of heterogeneous multiprocessors, and I expect that this is quite useful on mobile devices for many reasons that I discussed. And you can get both speedups and energy efficiency via parallelism, but the scheduling is not easy. And yeah, that concludes my presentation.
Okay, so could I have the panelists come up, please? Okay, could I have the slide?
Should we do down by one?
Okay.
Aren't you supposed to be here and I'm next to you?
So what we're going to do is we're going to have questions from the audience. That's you. So please queue up at the microphones, and you're welcome to ask questions of all the panelists up here. And they should be in order. Let's see. Good job, guys. Okay. All right. So, so any question is fair game, but please state who you are and your affiliation, and keep it a question, not a big long statement. And please ask a simple, brief question. Thanks. Go ahead.
Hi, Al Wegener with Samplify. I'm a little bit new to CUDA and OpenCL, but in the experience that I've had, taking conditionals out of code can help an awful lot. And aside from the simple select examples that I saw, do you guys each have different tricks or suggestions for those of us that are coding this up as to how we should structure our code so it parallelizes best?
Okay, so I guess I'll start and then we'll move down the line because we'll all have something similar to say but also some different things. So the select operator really was put in there to help you predicate code to basically avoid branching. I mean, that's fundamentally why it's there. The other thing that's often a better solution is when you really get into performance tuning is you do things sort of as Eric talked about, is you can rotate your data structures to prevent some of these issues from happening, sort of how you lay out your data, how you access your data, to help avoid branching. But branching is bad. Branching, besides being difficult for hardware, also breaks compiler optimizations. And when you get into fancy things like auto-vectorization or converting implicit parallelism into vector units, branching is going to throw the compiler for a loop, and that's where compilers are known to fail. And so you do effectively want to avoid branching. That's why there's the select thing. And if you can't rely on the select, then you're probably going to have to modify your data structures and your algorithm to avoid it.
Ditto.
Pretty much ditto. Compilers can try and predicate stuff for you and try and essentially use select for you, but you're either going to pay the cost of the branching divergence or pay the cost of doing twice the computation. So in general, you want to try and do data structure transformations that eliminate the amount of, sort of incoherence you have in your control flow.
I guess the one thing I would refine to add to that is that sometimes you can move the branches to a higher level of your algorithm where you're branching, and the branch will result in a large chunk of data that takes the same path that has locality in the work items. So maybe one work group will always take the same branch direction, and another work group will take another one, and you don't have decoherence on the hardware. So you can try and restructure your algorithms to take advantage of that.
Or even within a single work group, trying to hoist the incoherence to the highest level possible is going to be good.
Yep.
Sounds like a call for braided parallelism.
I'm not sure I'd go that far. But so another good example of that, which comes up frequently, and there's a bunch of good academic papers on this, is if you look at ray tracing on a GPU, if you do the naive implementation, that's like the worst possible thing you could do to a SIMD architecture. But with a little bit of manipulation, you can actually get amazingly good performance. Actually, at SIGGRAPH, there was papers, actually I guess technically it was high performance graphics, there were papers running on Nvidia hardware where they showed doing the transformations and the data structures to get good performance. The other big thing is when they knew they were going to get to some amount of being too divergent, they would actually stop the algorithm, resort, and re-execute to basically regain coherence, branch coherence on the outside of the algorithm.
Ramesh from Synopsys. I noticed in at least a couple of the talks there was a comment about the atomic operations and how you might use them in some global style, particularly given work groups kind of start and finish when the scheduler feels like. What kind of idioms do you see people using those in? At least some of the obvious ones I might try, I know will potentially deadlock and so on. So.
Yeah, so because you don't have the scheduling guarantee, you don't have a guarantee of forward progress, you have to make sure that you think about the deadlock possibilities when you use atomics. But there are a lot of really powerful algorithms that you can use and data structures you can use that don't require a specific ordering of the operations. So imagine you want to do a reduction sum type operation. You can use atomics to do that very efficiently by coordinating the work groups to, basically produce a partial sum when they finish, accumulating into a common result.
Yeah, one of the surefire ways to get yourself into trouble is to try to implement your own locking system using atomics. We've seen a bunch of people that have run on other architectures that will port to another one, and then it takes forever for them to figure out why things are deadlocked. I mean, synchronization is a big issue in parallel programming in general, and what we tried to do in OpenCL is the primitives that we give you should prevent you from getting into trouble unless you try to be too clever. And so, implementing complex semaphores using atomics, which require a scheduling guarantee, is going to break. But there's lots of other things that work just fine. I mean, we've seen lots of algorithms that effectively use transactions using compare and swap. But fundamentally, it's because they don't rely on the ordering. I mean, that's what atomics are meant for, is to give you a guarantee but on the correctness in memory, but not a guarantee on scheduling. So if you build things out of atomics that maintain that, you're going to be in a happy place. If you try to actually build hard locks, you're going to get yourself in trouble real quick. And although it may work on the architecture you're on, as soon as you move to another vendor's architecture, or even a vendor's architecture in the different family that's narrower or wider, it could break. So it's a pretty dangerous thing.
It kind of pushes you to go lock-free from the beginning with your data structures, which can also be good on a number of architectures.
It also pushes us to pay close attention to what people are doing with OpenCL, so we add the high-level synchronization constructs they need over time. Because I really agree with you. If people start building stuff, their own locking protocols, boy, they're asking for trouble.
Yeah, we actively discourage programmers from even thinking about writing locking protocols or using them if they already exist.
Yeah,
but this is one of the key areas where, so if there's something that can be presented to us as a motivating example for OpenCL 1.1, that we can figure out how to create a locking protocol that's going to work and keep people out of trouble, it's something we'd love to hear.
Absolutely.
Hello, I'm Susan Dickey. I work for UC Berkeley's Institute for Transportation Studies. And I'm interested in the OpenCL memory model where you've got these 4 different kinds of memory, the private, local, global constant, and host memory. How do you envision that in architectures of the future, like the kind of multi-core clustered with hypertransport and QPI that we just discussed this morning? How do you envision those categories being mapped to the memory hierarchy?
Good, a question that I think we get different answers from everybody on. So one of the reasons that we went in sort of the way that OpenCL has defined its memory model is sort of the realization that having programmers expect that a flat memory model and doing random access to a flat memory model is going to be successful in the future is a bad thing, and so OpenCL forces you to break out of that sort of right off the bat and concentrate on what your memory hierarchy will look like. In my personal view, OpenCL, it matches current architectures well, but it doesn't extend necessarily all that well into the deep cache hierarchies that may be coming on future cores. It doesn't take away, or it doesn't take into account NUMA awareness and other things, but these are things that have been discussed in the working group. As far as clusters, even with extremely fast interconnects, you still have a problem where OpenCL at its top level is a uniform address space as you get into global memory, and that's where things begin to get a little tricky on how that really maps. And yeah, you can use distributed shared virtual memory and all sorts of other tricks to do it, but there is an issue there in how we approach things. I mean, there's been arguments in the working group that an extended memory model, adding more hierarchies to the memory, and to be fair, this was my thesis work, so I am biased here, But extending more levels in memory hierarchy would allow us to adapt to progressively more complex machines. Should be noted, though, that it's going to put more weight on the programmer or a compiler and runtime system to then map that onto these complex machines.
Yeah, I think we have a lot to learn on exactly how these memory models are going to play out as we roll out OpenCL implementations. I mean, one thing that we've talked about in the group is we really don't have a formal definition of the detailed memory model. And I think we need to nail that down before we can really talk about extending it. But we do need to extend it because we know it's a given. Memory models are going to get more complex as time goes on.
I should mention, though, I do think we made the right call by having the memory consistency model be relaxed. And this might pick a fight with other architects in the community, but relying on coherence to scale is a dead end. And that's something we need to get over as well. And so having a memory model that actually says you must synchronize if you want guarantees allows us as architects to build way lower weight memory systems, much faster interconnects on the chip. So I think that is something we got right, but I think Tim's also correct where I'm not sure that we had the time or really had the experience to define the memory model itself and the hierarchies as tight as we would all like in the work group.
Yeah, I think we did get that right because, let's face it, we're friggin' brilliant. We got it right.
Yeah, so I think from NVIDIA's side, we want to see where things go. You know, OpenCL is kind of focused at the node level right now, and you know, being able to integrate with existing code is definitely a great thing. But as things go forward, you know, definitely I agree with you guys. It's the right stake in the ground to say relaxed coherency, explicit. So.
Yeah, I think once we extend past that individual node, we're in a whole different world where you've got a cloud of nodes somehow cooperating. When we start getting into asynchronous sort of things executing on different pieces of hardware, I'm not so sure that OpenCL addresses that yet, and we're going to have to think pretty hard about that before we can go there and probably get a lot more input from people that are doing that kind of computing than the kinds of computing that the working group has experience with now.
I'm Adam Bieberg. I'm here at Stanford. Across the 3 or 4 people that mentioned this, it was pretty consistent that you started out with an OpenCL implementation and it was about 1/4 or 1/5 the speed you eventually got. So there was a lot of work to change the algorithm and inputs, and then there was a lot of work, some of you pitched as tuning to the hardware. And like you guys to maybe comment, how much of that is changing algorithms, which is something programmers will just need to learn to program the new architecture, and how much is really legitimately Nvidia, AMD, cell, Larrabee differences that we'll still need to have 4 versions or 3 versions of our code for?
Another challenging question. So at least in our experience, there's a lot of architectures that rely on small vector, so SSE style things to be successful. And you're even seeing on the CPU side things get progressively wider with AVX and Larrabee native. So I think some of that is just going to stay because that's how you build efficient architectures. That's the best way we can get ALU densities in. But in many ways, the rest of the sort of high-level stuff is pretty similar. Launch fairly large work groups, beware of synchronization, avoid branching. There's a lot of things that are the same across all architectures. It's mainly arguments of, well, are you doing 128-bit access to improve your memory system, or do you need it to use your ALUs a certain way? So for architectures that may be scalar, you may get better memory patterns by using the wider formats anyways, just because they're going to coalesce much more naturally. I do agree with Tim that I think a lot of the sort of the vector stuff, at least for filling ALUs, we can fix with compiler work. Using compiler work to fix and do wide load stores is a very difficult thing. I've yet to see a compiler that can do that. The Cray one is the best I've seen, and it really struggles to do it. It has to do a tremendous amount of code manipulation, and usually it has to do a profiling run first, and then manipulate the structure of the code to get good data loads. But I think a lot of things are actually surprisingly common across architectures. But of course, there are going to be specific things to everybody.
Yeah, this is a problem that we've been struggling with across the history of parallel computing. And I think I think looking at how platforms are evolving and that there are a lot of similarities, we might be able to get it right this time, but it's too early to say. So I think realistically, programmers are just going to have to learn how to develop algorithms that can map across the different architectures, and they'll have to have lots of optimization knobs built into their code. As much as I'd love to see that go away, and I'm hoping we can minimize it, I think it's just something we're going to have to live with, which we've been living with all along anyway. So,
you know, I think I agree with a lot of what you talked about in your talk, Tim, that there's you know, a lot of choices that come with the OpenCL spec, but there is a path through there that, you know, I think hopefully we can, through hardware and compiler work, get to a fairly performance portable realm. But given how young OpenCL is, given that it was basically built to run on hardware that already exists, you know, today's programmers are going to have to deal with the knobs and the different paths.
I think I would add that, you know, your original question was, you know, how much of it is algorithmic work that they're just going to have to get over versus things that maybe the compiler can eventually fix. You know, I think one of the things that we consistently see is that the biggest speed-ups don't come from, you know, filling the ALUs and vectorizing. The biggest speed-ups come from dealing with memory bandwidth issues and data structure organizational issues. And fundamentally, doing that requires designing an algorithm in a different way. So I think at some level, you know, OpenCL is just exposing in a more explicit way to the programmers that you really have to think this other way if you want to have something that runs efficiently on modern hardware. I mean, the days where access to memory really was a small constant time, you know, are kind of long gone, and well, it's time for us to get over that.
So the other side of it, and we've begun to see code like this from ISVs, at least with the ones that we work with closely on our implementation, is because we can support both CPU and GPU, often what they end up doing is because the characteristics of what algorithms run where can differ, they essentially have a little micro benchmark thing they run at the beginning to figure out where to target and what application, or what device to choose. So we've seen a lot of stuff now where people have effectively stripped out sort of how the auto-tuning frameworks and Flame or Atlas work and are starting to put those in sort of the front end. So either at install or at first load, they do this along with saving off binaries and doing things that can reduce the startup time.
Gosh, that's ugly.
Gabriel Southern, should see what we used to do.
Oh no, I mean, I know we've been doing it and we will keep doing it, but can't we do something better?
Well, heterogeneity though is always going to be that problem, right?
Well, and it's why I think that OpenCL has such a bright future, is because at least we expose the information that you can plug into that kind of auto-tuner framework. So, yeah.
Okay. My name is Gabriel Southern from UC Santa Cruz. My question sort of about the development of OpenCL, and particularly the 1.0 implementation, and if you could compare it at all to CUDA. Sort of, I think a lot of things are similar, but there's other people on the panel sort of get, I guess, different opinions about what the differences or similarities are in terms of what it offers different from CUDA and what's similar and driven by that.
Chris, would you like to start? Would you like to you like to get yourself into trouble first?
Well, you know, I think the similarities start with the hardware that they were trying to sort of bring under the tent. You know, there was a realization that there was this piece of silicon on a lot of machines out there that was going underutilized. And that piece of silicon has a certain structure to it. That structure is evident in the way that CUDA exposes programming, NVIDIA GPUs, and it's sort of natural that a lot of similar constructs come out in an open standard as well, because you know, you're looking at the hardware that's already out there that you want to utilize. That being said, you know, OpenCL has as its primary target being something that's cross-vendor, that's open. So you know, it goes there and then goes beyond in a number of ways to make sure that you have the opportunity to see all the differences in the different vendors' hardware, that those are exposed in OpenCL in a way that you can adapt to. I'd say that's probably the primary difference between something like, say, CUDA and OpenCL, is that you know, OpenCL has this cross-vendor aspect to it that is part of its primary focus.
Yeah. I mean, in the end, so if you look at sort of all the data parallel languages, and more importantly, just the history of GPU in general. So you can go all the way back to 1978, so actually before I was born, with some of the first work done on the Khronos, one of the first GPUs built. And they were already doing these style algorithms on that core. And if you look at how that was done and how things came through sort of academia with SH and Brook and even some of the new stuff in OpenMP, you see a lot of these same trends kind of coming through. And so OpenCL, we kind of put a stake in the ground on sort of what we're going to try to encompass. And as Chris says, it is the architectures that are available today. And I think the biggest difference, frankly, between CUDA and OpenCL is at the moment, besides being cross-vendor, we've also taken on trying to support chips that have been supported by other things, so most notably cell and DSPs and then the embedded space. And then there's subtleties in the queuing model and everything else. But the other thing is, to be fair, OpenCL is very low level compared to some of the other things. So like Brook and SH are much higher level. CUDA is sort of a mix, so the CUDA driver API is much closer to the OpenCL API, but they also have some, in the CUDA model, there's some stuff above it that sort of abstracts a driver API from you. So there are differences. And so OpenCL really shot to, well, let's try to make something that will work across everybody's parallel devices in a fairly agnostic way as efficiently as possible. That was sort of the main goal.
I guess one direction is also the heterogeneous multiprocessing that the OpenCL tries to do, and I don't think CUDA even tried to address.
Yep. Maybe just building on that, a question. Obviously, you've declared today that this is a cross-platform, heterogeneously driven. This is where you wanted to go across all architectures. But quite clearly as well, it's been very obvious from the presentations, it's been heavily driven and is driven by the GPUs and the GPUs, which is understandable. But again, you guys are, and I think Tim played to it the most today, is you are playing to a fixed architecture. The other accelerator in the game here that probably is fairly high profile is the FPGA. Do you have any activity in your group looking at that and how the language is applicable to these devices?
So I've been talking quite a bit to FPGA people at Intel. And a lot of what we've been talking about, we're not ready to talk about in public, but the one thing I do talk about with them is that when they're building their FPGA infrastructure, one piece they need to build is the host device layer. And what I tell them is, look, use OpenCL for that. Don't invent a new API. And that's an obvious place, but it's amazing how many people get that obvious thing wrong. It was hard defining that piece of OpenCL. And please, any of you doing research systems of any kind with accelerators, use the one we created for that API. Beyond that, I really can't say anything.
I think the challenge is at the moment, looking at it from an FPGA side, OpenCL doesn't really seem to fit very well with FPGA.
I disagree. I mean, we've defined a very careful interface. We've defined a memory model that can encompass an FPGA. We've defined an extension of C that would be a fine kernel language for mapping onto an FPGA. I could see it working extremely well there.
Yeah, so one of the things we didn't talk about here, just for sort of lack of time, is so we did a lot of work actually to extend things. So there's a full attribute model, so sort of the GCC style attributes, you can tag things. For most people I've talked about on FPGAs, they're more worried about the dynamic launch characteristics of an ND range being user defined. However, in your kernel, you can actually say, I require this size workgroup, which allows an FPGA to fully flatten all the execution out and fully map it into the hardware. So, I mean, there were things that we did in the language to make this as easy as we could for an FPGA. But, I think we all know various companies are actually working on FPGA implementations, but none of us can actually say anything interesting.
I guess as a recommendation, and perhaps you ought to try to give a little bit of a portrayal of how you can bring the FPGA community in, because it does come outward as very GPU centric.
We have talked to several.
It comes across to me as very CPU centric.
Right. But the good news is we are talking to several FPGA-centric companies that have approached Khronos to join the working group, and that will be very welcome. The initial feedback, to kind of echo what's just been said, is on the first glance, the FPGA vendors are saying that there potentially is a good fit. So the high order bit is positive. But we do need their participation. So if any of you guys are FPGA vendors, please join and help us make sure that we evolve this in the right direction for you. Thanks.
Eric Sudlar from Oracle. And we've done some research with what you might think would be a lot of data parallel tasks in a database, and that's been tried for a long time on parallel machines, and I think that's going to push the boundaries a little bit of where GPU is, especially in the areas of synchronization, and also one of the things that's cool about SSE is horizontal operations. Now, the OpenCL standard seems to have taken a lowest common denominator approach, and as it tries to move forward, do you see it adding more optional features to kind of continue to evolve this type of computing to the next level, where I'd like to see it go, with some of those things that I think as vendors are working on fusing GPUs and CPUs, who shall remain nameless, are working on. Do you see that kind of this OpenCL trailing until like all of the vendors are doing it, or do you see like more optional features getting added? And what's kind of the sentiment among the OpenCL community for how do you push this forward without having to actually reveal any of your future ongoing plans, which I'm sure you'd have to kill us if you told us.
It is a stated goal of the group. We have occasionally we sit down and make sure we're all still in sync on what our high-level goals are. And it is a stated goal that we will enable the OpenCL standard to lead hardware by just the right amount. Now that's an art form in getting that the right amount figured out. But it's important that OpenCL isn't just capturing what's already been implemented in the hardware, and OpenCL plays a positive role in the industry to help bring hardware forward in a good direction that's good for the industry. Now, it's tricky to make that happen in practice. But I think we have the right players in the group to actually take a stab and actually help bring the hardware forward.
So the other side of that is, so one of the neat things about OpenCL compared to potentially some other things is that long ago with OpenGL we defined a nice way to do vendor extensions to then move into multi-vendor extensions, then into specs. And so there's some things that we just realized that we would have liked to have done in earlier specs that will already show up in later specs. There's other things that are more exploratory. So memory hierarchies were brought up. Well, there's been lots of talk, because various companies have more complex memory hierarchies of how to expose those. And to be quite honest, we don't have tremendously good ideas. So one of the best ways to do this is to shoot with a couple of different extensions from different vendors to see if we can find something that seems reasonable, and then we can latch onto it and then roll it into a spec later on. But I can tell you none of the silicon vendors are sitting still. I mean, so the spec is both pushing us and we're pushing the spec. Every vendor sort of has their favorite thing that they want in the spec, so their hardware really shines, everybody else gets screwed a little bit. No, I'm being honest, right? And then there's sort of the in-between. And the working group thus far has done pretty good about making sure that everybody gets to play, that everybody's silicon that's coming out is going to be okay. And thus far, we've done pretty good about not having to sort of show our cards too early. We basically get to say, I have a concern about this, and you look around, and hopefully somebody else has a concern, and then we bring it, and then we get the spec adjusted. And the same thing where it's like, the GPU vendors, for example, with upcoming hardware, there's extended requirements in the DX spec where we said, well, if everybody's going to be shipping hardware, maybe we want to rev things up in an upcoming release because everybody has it anyways. So there's good things like that.
The other thing that we have, of course, is not everyone at the table is a hardware vendor. So we try to also get input that pushes what people on the development side of the community might want in the future, and then we have vigorous discussion about whether or not that's actually possible.
Yeah, and to that point, there's actually a large upcoming feature that was purely driven by the software companies.
So, and of course, if there are other software companies out there that want to join the committee and help push the future of what people want for programming, we'd welcome you to do so.
Yes, please do. It also gives you a way to drive the silicon vendors to do what you need.
Well, so one place where that hasn't really happened yet was SSE, where it's really only kind of showing off part of the power of SSE, right? Mm-hmm. So, I mean, you could have put in some features in OpenCL that would, via some vendor extension, allow that to, get into the spec and say, oh, okay, if I'm running on an SSE thing, and maybe that's going to be a Larrabee in the future, or that's an AVX, or whatever the next thing is after that. I mean, there are some things in there which, might be, vendor specific for a while, and you guys haven't done that yet. So.
Yeah, so implementations are just coming up. So expect to see extensions coming sort of after implementations kind of settle a little bit, and then sort of as everybody's happy with it, and there's more importantly a proven need for it, then that's when the conversation occurs on when it goes in the spec. So like cross-vector communication, for example, is something that was talked about, but not everybody's silicon could do it for CL10.
So you'll see more of that in the future then?
You're going to see more vendor extensions moving into core spec, yeah.
Thanks.
Yeah, so I'm Chad Austin from IMVU, and I was wondering, so let's say I'm shipping software on Windows, and I want to use OpenCL, and I want to use it on sort of all of my users' machines, and I noticed that sort of everybody has their own implementation. What's the deployment plan for just like shipping software that works?
Thank you for asking. That's an excellent question. So the solution to this is something called an installable client driver that the working group is working towards defining a specification for that we intend to participate in that basically allows you to abstract the OpenCL API between different vendors' installations.
Yeah, sort of
like OpenGL.
Yeah, the best way to think about it is like OpenGL, right? So you code the OpenGL interface, and as long as the user has something that supports OpenGL, it runs. This is a very similar idea, where so there's a single sort of OpenCL DLL that you link against, and then that abstracts the different vendors' implementations.
So let's say I've got an Nvidia GPU and there's an optimized Intel implementation. Those will work together.
You should be able to use both.
Yeah.
That's the intent.
Yeah. Great. Thanks.
All right. So that question actually broached the topic quite nicely, which is that. So there's
Could you state your name, please?
Oh, sorry. David Cantor from Real World Tech. So that question sort of broached the topic of other software companies, or I'll just be really specific. So Microsoft has sort of their own notion of how they'd like to handle compute through the DirectX compute shader. And I'm kind of curious how you anticipate working with that, and also in terms of, do you see that OpenCL is sort of a venue to push or pull and work in the right direction? Because it seems like in addition to leading hardware vendors, you're also leading perhaps to some extent alternative software models.
Well, I think we feel like we have a pretty good model with where we tread with OpenGL in terms of interoperability, so that basically there's a way of interfacing another model with the OpenCL model, and I think that we would expect that to work for other compute specs as well to some extent.
But also I think on Windows systems, even though there is direct compute, just like OpenGL ships on Windows systems as an alternative to Direct3D, the same thing will happen with OpenCL.
Yeah, so where was the demo running?
What? I'm sorry.
What was the demo running on?
The demo was running on Windows 7 with OpenGL and OpenCL.
I guess I would add that, I think we're going to try and push as much as we can for implementations to be available on all platforms that interact with everything we need it to. From the point of view of software developer, we're interested in a common platform, and we'll try and have conversations to make sure that happens.
And so at GDC, we actually showed OpenCL interoperating with DX10 on Windows Vista. We've also showed DX9 interop as well on XP. So as Chris said, our goal is to make OpenCL interoperate the best we can with other things available.
Yeah.
The primary goal here is to enable developers. It's not a competition with other technologies. It's not the primary goal.
Lisa Ando, I represent myself. From the last two speakers, it is not like, say, writing one OpenCL code and be done with multiple platforms. You need a lot of tuning, right? And so my question is that, say, supporting two platforms, how much effort do you need, 1.9 or 1.1?
Well, let me first just briefly comment that if I was writing, say, a C++ program, and I wanted to move it around to different architectures, I'd have to do a whole bunch of tuning as well. So tuning is just a fact of life when you care about performance. And is it worse for OpenCL as opposed to outside OpenCL? I don't know. I don't think it necessarily is.
I think I can address that to some extent. I mean, I've personally moved a lot of code around some very hard to program on embedded systems for performance. And, lots of people in our company that were involved with the experiments we did have. The difference that I would say between my experience with OpenCL and some previous systems are, and a lot of the previous systems, once you've optimized code, you kind of get something that I refer to as write-only code, because you're never going to be able to read it again. And even worse, if you decide that you want a different algorithm, you start at square one again. You have to rewrite it from the ground up, re-optimize, design everything over again. Whereas, what we've seen so far with OpenCL is you at least get code that, one, you can generally understand by reading it, and two, you can modify that code in place to tune it for another platform. So the kernels in the demo that I showed that vary between the vector and the scalar, and there's actually some other ones hidden that I didn't really talk about, other variants. In a lot of cases, those variants were actually done just by if-defs in the code. And where they weren't done by if-defs, they're still substantially similar. So I think it's in a better place than we were. Is it ideal? By no means. I would love magic compilers as much as the next person. But it's a lot better place, I think, than where we were in the past.
Yeah, I'd like to emphasize something that with OpenCL, we exposed everything. I mean, well, maybe everything's too broad of a word, but you can query the compute device and learn a huge amount about the characteristics of that compute device. Now move outside of OpenCL to other environments, like, well, OpenMP, another favorite of mine. None of that's exposed. None of it. You have to kind of guess or trick the compiler to do what you want to do, or some other ass-backward sort of thing. It's crazy. So in some ways, I think OpenCL might, and I say might because I haven't written a lot of code yet, but I think OpenCL might actually turn out to be easier in the long run for the tuning step, which still has to happen, but at least all the knobs are exposed. You don't have to guess at them. They're all exposed for you. And I think as a software developer, I know for me from the HPC world, I like that a lot.
So I think the other important thing, it actually came up in a lot of the talks, is that the first order effect, which is optimizing your memory usage behavior, is basically identical for all the shipping things. And that's, frankly, the two places where you spend all your time, really, writing the code are first, manipulating your algorithm into data parallel, if you're going to choose the data parallel version of it, and then fixing your data structures to be better laid out in memory and better for access. Once you've done those two things, you have a fair amount of performance portability between at least the multiple implementations I've tried thus far, including ones outside of the ones that we have. But yeah, when you get down to that last 40% or sometimes just the last 10%, yeah, I mean, you're down into, oh, I need to schedule these vectors right, or I need to add attributes to get the compiler to do the right thing here. So a lot of the first order stuff, I think you're going to get it. More importantly, and I think this is really the first sort of parallel programming language I've seen that is actually device portable. OpenMP surely is not. Right. MPI surely is not. pthread surely is not. And this is actually something where you've seen code running on GPU and CPU, and I can tell you from experience that we've moved code between CPU and GPU implementations, and A, it worked, which was huge. And then once we told people sort of the commonalities between CPU and GPU, the performance is actually pretty good on each platform.
It might have been a subtle point in the demo I was running, but at one point I hit a key and it switched from CPU to GPU. That would have been a lot harder to implement in a handwritten sort of scheme.
May I ask a comment from Kari? What do you think? How useful will OpenCL be?
Well, about these optimization parts, I think lots of these things that knobs are exposed, so everything is, you kind of can more easily enumerate all the options that you have that you need to you might need to do,
optimize your algorithm to one particular hardware. So because you have made these things uniform, you could imagine that you kind of do this profiling part first, and then adapt the allocation of the kernels to different processing elements and so forth. The compiler might be able to do that, and in general, you shouldn't have to. The kernels themselves would not need to be changed much. So I think this optimization actually with this kind of system, well, as like everybody else said, it's way easier than the alternative doing without OpenCL.
I think one other thing that may not be obvious is that the entire host implementation is a large piece of infrastructure that lets you even go about scheduling this work. And without this system in place, you end up having to implement all of that kind of infrastructure around your algorithm. And that's a non-trivial piece of work. And if it's different for every platform you've got, and maybe even different for every algorithm you've got because it was a different guy that wrote it, you get in all kinds of trouble where maybe you can't mix two algorithms that two separate teams wrote because, hey, they wrote a different infrastructure for scheduling, and I can't move it from platform A to platform B because the way I designed that scheduling algorithm on platform A is impossible to run on platform B. That common host infrastructure is actually a huge step up for a lot of the kind of work that we have to do initially just to get things running.
Thank you.
Okay, so we need to wrap up. Let's thank our speakers.